Hello dear students, I am Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to cover the full solution chapter. And you know what? From the solution chapter, every year in your NEET examination, you get at least 2 questions. So after watching this video, you can be sure that you will be able to solve those questions that you will get in your NEET examination. Students, you know what? In the NEET examination, from the solution chapter, we get questions mostly from the topics like one-top factor, colligative properties, Raoult's law, Henry's law. So all those topics I have covered in this video, and also I have covered that what type of question you can get from those topics. You know what? Whenever you study any topic, so you need to analyze that topic, that from this point, what type of questions I can get. So I have done that in this video. Also, you know very well that in the description section, I have provided DPP practice sheets for you, right? And you need to complete them. Students, if you complete all the questions from the DPP, believe me, you can be 100% sure that you will solve each and every problem that you may get in your NEET examination. And anytime you can check that. Practice the full DPP and after that attempt the PYQs questions of the NEET examination. And also, you know very well that those DPPs, those practice sheets you can get on the PW app, where many lakhs of students are preparing, right? And they are taking the help of PW app. So from the app also, you can download the DPPs, the practice sheets. Now, the very first thing is, as I told you, I will tell you how you can remember the whole concept of this chapter. Now, what can be done here? The whole chapter can be memorized, can be remembered in 3 parts. You can divide the full chapter, you can divide the whole solution chapter into 3 parts, like overall in this chapter, we have to discuss 3 different types of solution. 3 different types of solution. One will be gas in liquid solution. Second will be liquid in liquid solution. And third will be solid in liquid solution. So there are many more types of solutions are there according to phase. Very soon you are going to see that. But our focus will be mainly on these 3 types of solution. One is gas in liquid solution, one is liquid in liquid solution, and one is solid in liquid solution. Now, under this topic, gas in liquid solution, you have to discuss, you have to study mainly 2 topics. One is how the solubility of gas is affected by different factors. So we will be discussing about what are the factors on which solubility of gases in liquid depends upon. And then we will discuss about Henry's law and what types of question we get from the Henry's law. So overall you can say that inside this gas in liquid solution, we have to talk about mainly 2 topics. One is solubility of gas and the other one is Henry's law. Now, talking about the second part, that means liquid in liquid solution. In this also, you have to discuss mainly 2 topics, right? In liquid, the first topic will be obviously Raoult's law. This is very important, students. Most of the times in your NEET exam, you get questions from Raoult's law. So inside liquid solution topic, we will be talking about Raoult's law. What is Raoult's law? We will see many numerical questions from this. And after Raoult's law, we will talk about what are ideal and non-ideal solutions. Ideal and non-ideal solution. So inside this liquid and liquid solution topic also, we have 2 points. And same goes for the third part. When you talk about solid in liquid solution, so in this part also, you have mainly 2 topics. One is the most important one again, colligative properties. We have to see what is colligative property, what are the types of colligative properties, what are the formulas in it. And then we will see lots of numerical questions from the colligative properties. And after colligative properties, we have another point here, which is again very important, and it is also used in the colligative property part, and it is one-top factor. So what you can do here, the whole solution chapter, you can remember in 3 parts: gas liquid, liquid liquid, and solid liquid. And in each part, you have 2 topics to discuss. right? Henry's law, solubility of gas, Raoult's law, ideal non-ideal solution, colligative property and Van 't Hoff factor. Now, apart from all these topics, apart from all these three parts, one more point is there, which is concentration terms. You can say that concentration terms in this chapter, they are kind of prerequisite. Whatever topic you discuss, in every part, you require the knowledge of concentration terms. But I hope students, you all know concentration terms very well from your class 11th first chapter. That means some basic concepts of chemistry, right? But we will also talk about concentration terms because it is also there inside the solution chapter. So you can say that concentration term is a repeated topic in our solution chapter, right? Now, so overall you can say these three are the main part, but side by side we have to look into the topic that is concentration terms. And that's how we memorize the whole chapter, right? Now, let's see quickly what are the topics we will be covering in this session, in this video. Obviously, our topic will be according to those three classification of gas, liquid, liquid and solid liquid solution. So, we will be talking about introduction of solution first. We will see what is the meaning of solution. Then we will be talking about concentration terms. I told you concentration terms we have already seen in the class 11th. But still we are going to again repeat all the concentration terms. Then we will look into what are the factors on which solubility of gas depends, then Henry's law, then vapor pressure. Again, let me tell you, when you go into the liquid solution part, so in the liquid solution part, you will be talking about Raoult's law, ideal, non-ideal solution, azeotropes and all. But in that part, the most important topic is vapor pressure. So you need to always focus on the vapor pressure part. So vapor pressure, then Raoult's law, then we will see what is ideal and non-ideal solution, and finally we will move into the solid liquid solution part. There again you will see what are the factors on which solubility of solid depends in liquid, and then finally colligative properties and of course Van 't Hoff factor. So these are the topics which we will be covering in this session, in this video. So now students, let's see the first point of our chapter, that is what is the meaning of solution. What do you mean by solution? I hope that from your childhood itself, you know what is solution. Every day you are looking at solution in your life. Like suppose the most common example is salt water. As soon as you put salt in water, that becomes a solution. But when you talk about what will be the definition of solution, so solution can be defined as homogeneous mixture. Okay, so homogeneous mixture of what? Homogeneous mixture of two or more compounds. And what do we mean by homogeneous mixture? A mixture in which the constituent particles are uniformly distributed. Now again, one very important point. Homogeneous mixture can contain two or more compounds. But in this chapter, we talk about only that mixture which has two components. And whenever a homogeneous mixture has two components, so then it is called as binary solution. So throughout the chapter, we will be talking about only binary solution. Similarly, if your solution has three components, it is called ternary, quaternary and so on. But we are not going into that three component or four component solutions. We will be talking about only binary solution in our chapter. Right? So solution is homogeneous mixture, and in this chapter we will be talking about what? Binary solution. Now again, because the binary solution has only two components, let's say that one component is A, one compound is A, and that is mixed with another compound B. So you should know that when we have two compounds in the solution, in the mixture, one of them is called as solute, and at the same time the other compound is called as what? Solvent. So out of two compounds, one is your solute and one is your solvent. And you know very well that the the compound which is present in lesser amount, that we call as solute, and the one which is present in excess amount, so that compound we call it as solvent. So now you know what is solution, what is solute, what is solvent. Solute is in less amount and solvent is in more or excess amount. So after understanding the basic part, that what is solution, now let's talk about a topic which is easy, but many times many students skip that part. Please don't do it, because in your NEET examination many times you get direct question from this. Students, what we have to do, we have to classify our solution according to the phase, according to the state. See, I told you that our binary solution, it will have a solute and it will have solvent, correct? Now, out of those solute solvent, their phases can be different. Like for solute, we can have gaseous, liquid, solid, all the three phases. And for solvent, we can have again three phases, gases, liquid or solid. So point is this, according to the phase of, according to the state of solute and solvent, we can classify our solution into total 9 types, 9 categories. One is called as gaseous solution. So now gaseous solution means when your solvent is a gas, correct? So whether your solute is gas, liquid or solid, if the solvent is gas, then the solution overall is called as gaseous solution. So what we can say here, that solution is mainly classified according to the phase of what? Solvent, or solution is named according to the phase of solvent. If solvent is gas, then it is gaseous solution. If solvent is liquid, then it is called liquid solution. If your solvent is solid, then it is called what? Solid solution. But again, for gaseous solvent, we can have 3 different phases of solute. One is gas, one is liquid and one is solid. So first one is gas in gas solution, second one is liquid in gas solution, third one is solid in gas solution. Similarly, when it comes to liquid solutions, so here also we have 3 types: gas in liquid solution, liquid in liquid solution, solid in liquid solution. And same goes for the solid solutions, right? When we have solid solutions where solvent is solid, so there we have 3 cases. Solute can be gas, solute can be liquid, or solute can be solid. So gas in solid solution, liquid in solid solution and solid in solid solution. But as you saw right earlier during the mind map, during when I told you that how you can remember the chapter, how you can memorize the chapter, so there you must have noticed that in the chapter we mainly focus on the liquid solutions. Our chapter mainly focuses on the liquid solution, gas in liquid, liquid in liquid and solid in liquid. Now in the examination, most of the time they ask about the examples of these solutions. So at least 1 or 2 examples of each cases you should know, you should remember, right? And if you don't know, please note it down in your notebook. Like when it comes to gas solution, so here you can take example of atmospheric gases. Students, you know that in our atmosphere we have oxygen, we have nitrogen. So mixture of oxygen gas, nitrogen gas can be one of the example of gas solution. You can take other examples also like helium oxygen, helium nitrogen and so on. And always remember that whenever you mix 2 ideal gases, so gaseous mixture is always homogeneous. Done? Now if you talk about liquid gas solution, that means what? When your solute is liquid and your solvent is gas. So one of the example of this can be given as, I hope you all know chloroform, right? And if chloroform is present in your environment and it is mixed with the nitrogen gas, so chloroform, which is a liquid, if it is mixed with any gas like nitrogen, so this can be example of liquid in gas solution. And if you talk about solid in gas solution, so most famous, most common example can be smoke. Students, smoke has mainly gases, a gaseous environment, and in that environment a small solid particles are present. So smoke can be one of the example of solid in gas solution. Now talking about the liquid solution, their examples are very easy. I hope you must be already knowing the examples of at least liquid solution. Like when you talk about gas in liquid solution, so it can be oxygen present or dissolved in water, right? So oxygen plus water, oxygen is solute here and water is solvent here. If you talk about liquid solution, so we have plenty of examples for liquid solution like ethanol water, methanol water, right? So here I am writing what? Ethanol C2H5OH plus water. It is example of liquid solution. And again, when it comes to solid liquid solution, like you can say sugar plus water, glucose plus water, right? Salt plus water. They all are the examples of solid liquid solution. And finally, the most interesting one is when your solvent is solid, right? So in this case, we have gas in solid solution, and for this, the example can be from your organic chemistry, students. I hope in your organic chemistry, you must have discussed about hydrogenation reaction or catalytic hydrogenation. So during catalytic hydrogenation, what you do, you take hydrogen and you take nickel, platinum or palladium. So that can be one of the example of this gas in solid solution. In gas and solid solution, I can take hydrogen present in palladium. So here palladium is your solvent, and hydrogen is gas which is solute. And when it comes to liquid in solid solution, students, so here the best example can be amalgam. You know what amalgam? Amalgam is a mixture of any metal with mercury. Now the point is, mercury itself, it is in liquid state. So with mercury, when you mix any other metal like sodium or zinc, so sodium or zinc can be solid, that will be your solvent, and here mercury will be your solute. And finally, if you talk about solid solution, so you can take example of any of the alloy. All the alloys are there, they are the examples of solid solution like brass, bronze and all. So point is this, do not skip this classification part, right? Do not skip this because you will be getting questions from this in your exam. So take your pen, paper and brain again and try to solve this question, a very simple question from the topic that is types of solution. Can you do it, all of you? We have two lists here. In one side you can see we have some examples like humidity, alloys, amalgam, smoke, and on the other side we have types of solution. Solid in solid, liquid in gas, solid in gas, liquid in solid. So you have to do the matching, correct? I hope you all are doing this question because this is very fundamental question, and just now I explained it. What is the meaning of different types of solution? So here, what is the meaning of humidity? Students, humidity means small droplets of water present in your gaseous environment. So humidity can be example of liquid in gas solution. Liquid in gas solution. So A can match with 2. If you talk about alloys, just now I told you that alloys, that means mixture of 2 or more metals homogeneously. All the alloys are examples of what? Solid in solid solution. So alloys can be matched with the first part, that means solid in solid solution. And amalgam also, just now I have told you that amalgam is an example of liquid in solid solution. So this will matched with fourth one, that means liquid in solid solution. And finally smoke, right? Even this example I gave you, that smoke is example of when solids are present in large amount of gases. So here the matching will be A with 2, B with 1, C with 4 and D with 3. And if you check the answer, definitely it will be A matched with 2, B with 1, C with 4 and finally D with 3. And you know what, students? This question, this easy question, this came in your NEET examination, NEET 2025. Now that's the reason I am telling you that you need to focus on types of solution, correct? Now quickly moving to the next part, because I hope now you will follow the topic types of solution also apart from the rest of the chapter. So let's quickly move on to the next part, which is concentration terms, because see, I know you concentration term you studied in your 11th class, right? All the concentration terms. But here what you can do a quick revision, because this is a prerequisite. In the rest part of chapter, again and again you will have to use all the concentration terms, molarity, molality, mole fraction, especially these three, molarity, molality and mole fraction. So point is, first thing is, what is the meaning of concentration term? Students, concentration terms, please always remember that it is a kind of a comparison of amount. Concentration term is nothing but a comparison. Comparison of what? Comparison of amount. Amount of what? Amount of solute and solvent and solution. So when you compare amount of solute with rest solvent and solution amounts, so that is called as concentration terms, right? So always remember that all the concentration terms, they are just a comparison term. And here we mainly focus on the comparison of solute and in some cases the comparison of solvent. So whenever you are doing comparison of amount of solute, so students, amount of solute can be compared only by two parameters. Either solute can be compared by solvent or it can be compared by what? Solution. Done? Either solvent or solution. And here see, mathematically comparison means what? Comparison means division. So all the concentration terms, if you look at the formulas of it, so it is like amount of solute divided by amount of solvent or amount of solution. Now with that, let's talk about the very first concentration term, that is molarity. And it is one of the most used concentration term in our chemistry, throughout chemistry. So students, what is molarity? Denoted by capital M. You can calculate molarity as number of moles of solute divided by volume of solution in liter, right? So it's a kind of comparison, right? In the numerator you are taking amount of solute and in the denominator you are taking amount of solution, right? But in different units, not in the same units. In the numerator solute is taken in the units of mole and in the denominator solution is taken in the units of liter, right? So molarity is number of moles of solute per unit or per liter of solution, correct? And if you talk about what will be the unit of molarity, so always it will be mole per liter, mole per liter. One more thing students, please focus here, because molarity depends on volume, so please remember that molarity will also depend on temperature. Molarity will also depend on temperature. Because sometimes in the examination, people will ask you that which of the concentration term will depend on temperature and which will not. So any concentration term, if it is depending on volume, so that means it will depend on temperature also. So molarity will be dependent on temperature. Now, after molarity, which is number of moles of solute per liter of solution, the second most common concentration term we have is molality, and molality is denoted by what? Small m. And if you look at the formula of molality, students, so it is moles of solute divided by mass of solvent, and the mass of solvent you will be taking in kilogram. So again, molality is also a comparison term, and here you do comparison of solute with solvent. Solute with solvent. In the numerator, you take solute, amount of solute, but in the units of mole. And in the denominator, you take solvent, you take amount of solvent, but in the unit of what? Kilogram. And if you talk about molality, so its unit will be what? Mole per kilogram. And because it is not depending on volume, so it will be independent of temperature. So molarity is temperature dependent. At the same time, molality is temperature independent. And what you need to know here, you should be able to do the calculation of all concentration terms. Like see, for any solution, if the informations are given, if the information regarding amount of solute, amount of solvent, amount of solution, it is given. So if the information of solution is given, so from that you should be able to calculate molarity, molality and rest of the concentration term. That is the requirement for solution chapter. That's the requirement of solution chapter. Now, after molarity, the next most used concentration term in this chapter will be mole fraction, which is denoted by chi, Students, for mole fraction, one thing is completely different, and that thing is mole fraction can be calculated for both solute and solvent. Normally, when you calculate molality or any other concentration term, so that is calculated with respect to solute, that is calculated for solute. But mole fraction, this term can be calculated for solute as well as solvent, right? Now, when you try to calculate mole fraction of solute, so mole fraction of solute will be moles of solute divided by the total mole of solution. Now, total mole of solution can be calculated as moles of solute plus moles of solvent. Moles of solute plus moles of solvent. In the same way, if you try to calculate mole fraction of solvent, so for solvent mole fraction will be moles of solvent divided by total mole of solution. That means moles of solute plus moles of solvent. And if you talk about what will be the unit of mole fraction, so because in case of mole fraction, both the numerator denominator have the unit same, that is mole. So mole will be cancelled out, and for mole fraction you will have no unit, or it is a unit less parameter. Now, one more important point, especially for the solution chapter, which you will be using in the upcoming topic, that is Raoult's law and all, is always remember that mole fraction of solute plus mole fraction of solvent is equals to 1 always. You can verify that just by substituting the formulas. But always remember that mole fraction of solute plus mole fraction of solvent will be equals to 1. Right? So always keep in mind, in the solution chapter, these three are the most used concentration term: molarity, molality and mole fraction. Now, apart from these three, we have few more concentration terms, like one of them is percent by mass, and it is also written as percent W by W, weight by weight. Now, what is percent by mass? Percent by mass is mass of solute divided by mass of solution, and because it is a percentage term, so into 100. Now, when you are calculating percentage by mass, keep in mind that the unit of solute and solution's mass should be same. Like if you are taking solute in gram, then the weight of solution should be in gram. If you are taking solute in kilogram, then the mass of solution should be in kilogram only. Right? So that's how you will be calculating what? Percentage by mass. Just like percentage by mass or percentage W by W, we have few more terms. Like one is percentage by volume. I hope that if you have understood percentage by mass, you must have automatically understood what will be the meaning of percentage by volume. Students, percentage by volume means you take volume of solute, you divide it by volume of solution, and then because again it is a percentage term, so multiply by 100. Right? And again you will have to take the same unit for both solute and solution. So volume of solute in ml divided by volume of solution in ml into 100, or volume of solute in liter upon volume of solution in liter into 100. That will be the formula for percentage by volume, and it is also written as percentage V by V. Then we have a slightly different term from percentage by mass and percentage by volume, and it is percentage mass by volume. Now, in the case of percentage mass by volume, what you do? You take solute in the terms of mass, but you take solution in terms of volume. So the formula of percentage mass by volume will be mass of solute divided by volume of solution into 100. And here you need to be a little bit careful regarding your units. When you are calculating percentage mass by volume or percentage W by V, weight by volume, so you take mass of solute and you take volume of solution. Point is, if you take mass of solute in gram, then you should take volume of solution in ml. And if you take mass of solute in kilogram, then you should take volume of solution in liter. And of course, again it is a percentage term. So for percentage multiplied by 100. So like this, you can calculate all of these concentration terms. Now, after this, we have two more concentration term. One is parts per million. Parts per million, in short, we call it ppm. But please remember always that parts per million is quite similar to percentage by mass or percentage by volume. Students, you need to understand this here. Percentage, fraction and ppm, all of they are similar kind of terms. Percentage, fraction and ppm. You know what? When you say percentage, so percentage means anything out of 100, right? If a solution is 500 gram and it has 5 gram of solute in it, so there you can say 500 gram of solution has 5 gram of solute. So if you want to calculate percentage of solute, so you will have to calculate that out of 100 gram of solution, how much solute is there. So when you calculate anything out of 100 part of solution, it is called percentage. Similarly, when it comes to fraction, so fraction is what? Fraction is out of 1. Means when you calculate amount of solute out of 1 part of solution, right? In 1 gram of solution, whatever gram of solute is there, so that will be called as fractional mass of solute. So percentage is out of 100, fraction is out of 1, and similarly ppm, parts per million, is out of 10 to the power 6, out of 10 to the power 6 part of solution. Correct? Now suppose that if a solution is there in which mass of solution is this, W of solution, and mass of solute is this, W of solute. So just use unitary method here. Yes, unitary method. You can say that this much amount of solution has this much amount of solute. So one part of solution will have weight of solute upon weight of solution. This much part of solute. So 10 to the power 6 part of solution will have this upon this into 10 power 6, this much part of solute. Right? So weight of solute upon weight of solution into 10 power 6 gives you the ppm, gives you the concentration of solute in terms of ppm. And again, please note down that here weight of solute and weight of solution should have the same unit. Not only this, ppm can also be calculated in terms of volume. ppm can be calculated like volume of solute upon volume of solution into 10 to the power 6. But please always remember this thing, that percentage, fraction and ppm, they are kind of similar terms. Percentage out of 100, fraction out of 1 and ppm out of 10 power 6. In the same way, you can say about ppb, parts per billion. Parts per billion is out of 10 to the power 9. So if you calculate ppb, so in that case here instead of 10 to the power 6, you will be having 10 to the power 9. Correct? And after ppm, the last concentration term is normality, which is a very special concentration term for students, because many of the students, they struggle with normality. But believe me, it is just a myth for you. If you feel that normality is difficult, believe me, you are wrong. Because normality, students, it is quite similar to molarity. Normality is similar to molarity. The only difference is when you calculate molarity, so there you take amount of solute in the units of mole divided by volume of solution in liter. Now, if you calculate normality, so in this case, the solute instead of mole, it is taken in the units of gram equivalent. In the units of gram equivalent. That's the difference. In molarity, we have mole. In normality, we have equivalent. Divided by here also volume of solution in liter. And I hope you know that the mole unit and gram equivalent unit, they can be converted or interchanged with help of n factor. Gram equivalent or equivalent is equals to mole into n factor. Gram equivalent is whatever number of mole is there multiplied by n factor. Right? And Because equivalent and n factors are related, so in the same way normality and molarities are also related. We have similar kind of formula for normality, molarity. Equivalent is mole into n factor. Similarly, normality equals to what? Molarity into n factor. Please note it down because these formulas you need for this chapter, and even when you talk about the electrochemistry chapter from class 12th. In electrochemistry, you need to have knowledge regarding mole, gram equivalent, normality and molarity. Correct? So, students, these are the concentration terms. At least their formulas and definitions you should know, and you should be able to calculate all the concentration terms for any solution. So now take your pen paper, because what we are going to do, we are going to quickly solve few problems from concentration terms. And I want you to do it first. I want you to do it before me, always, always. Any question is there. So in this question, and please pause this video, solve it. Later on you can match the solution. You can see the answer, you can match the answer. So question is, calculate the mole fraction of aqueous ethylene glycol in a solution which contains 20% of ethylene glycol C2H6O2 by mass. Correct? So if you look at this problem, the main target here, always focus on the target. The main target here is to calculate mole fraction. Now again, mole fraction can be calculated for both solute and solvent. So in this case, we have to calculate mole fraction of what? Mole fraction of ethylene glycol. That means our solute. So just apply the formula. Students, for mole fraction of ethylene glycol, that means C2H6O2, you can say that it will be moles of ethylene glycol, C2H6O2, divided by moles of again ethylene glycol plus moles of what? Moles of solvent. Now here please notice they have mentioned aqueous solution. Now you should be able to understand when you say aqueous solution, that means here solvent is water. Here solvent is water. Right? So moles of solute upon moles of solute plus moles of solvent. Because solvent is water here, so I will be writing moles of water. Done? Now just calculate the moles and substitute, you will get your mole fraction. The information regarding solution they have given is, it is 20% by mass. See, although percentage by mass, percentage mass by volume, they are the concentration terms, but you can regard them as information. Always regard percentage mass as an information for you. See, if they are saying that ethylene glycol is 20% by mass, so this means what? If I take solution, if I take my solution 100 gram, so out of 100 gram, the solute will be 20%, that means 20 gram. And at the same time, if I talk about solvent, so solvent will be 100 minus 20, that means what? 80 gram. So now I have all the masses, solution, solute and solvent. And I can easily calculate mole, because you know what? Mole is what? Given mass by molar mass. So if I calculate number of moles of ethylene glycol C2H6O2, so that will be mass of solute, mass of ethylene glycol 20 gram divided by molar mass of ethylene glycol, and molar mass of this you can calculate by the magnitude of molecular mass. C2 means 24, H6 means 6, O2 means 32. So 24 plus 6, 30, 30 plus 32 is 62. So molar mass of ethylene glycol is 62. So number of moles will be 20 upon 62. Correct? And then finally, if you talk about number of moles of solvent, water, so water's given mass is how much? Solvent is 80 gram here. And for water, I think you all remember that for water molar mass is 18. So 80 upon 18. Now I think you can solve it, right? Number of moles of solute and solvent, both you have. Just substitute here, you will get your answer, right? And if you have done, please match your answer, because the answer will be 0.068. Students, you need to be very good in your calculations. Now, again we have another question from concentration term, but I want you to do this first. This is a very simple, you can say direct problem. all the information regarding the solution is given, and you have to do just the calculation of concentration terms, right? Pause it, do it by your own first. I am doing because I have to solve it, right? You pause it, you do it first. So question is calculate molarity. So we have to find out molarity. 5 gram of NaOH is given, so that means the solute, the NaOH is 5 gram, and for solution they have given the volume also. So I think everything is given in this problem, right? Because mass of solute is given 5 gram, we can easily find out the number of moles of solute. Here mole can be represented by small n, n means mole, so moles of solute will be given mass 5 divided by, for NaOH students, if you calculate molar mass, so sodium atomic mass is 23, oxygen 16, hydrogen 1. So 23 plus 16 plus 1, it will come out 40. It will come out 40. So 5 upon 40, it will be 1 upon 8. So 1 upon 8 is the number of mole of solute in this. And volume of solution is already given 450 ml. So if you convert that into liter, so you can say volume of solution will be 450 upon 1000, that means 0.45 liter. One more thing is, you need to be good in the unit conversion part. You should do them very quickly, gram, kilogram, mole, equivalent, liter, ml. Unit conversion part should be very, very strong for you if you want to do good in your concentration terms part. And you know that you need to have good skills in calculating the concentration term. You should be very good at concentration term, because in each and every part of solution we need it. So volume we have, mole we have, we can find molarity now, because molarity is number of mole of solute, which is 1 upon 8 divided by volume of solution in liter, which is 0.45. I hope you can do the further calculation. I am not doing it, but just to confirm you, your answer will be here 0.2788. It will be roughly 0.27777, but if you round off, you can write it 0.278. So now I think at least the basic part or the direct problems of concentration term you can solve. And please always remember the formulas of concentration terms. Can you do one more question, all of you? How many grams of concentrated nitric acid solution should be used to prepare 250 ml of 2 molar HNO3? The concentrated nitric acid is 70% by mass. They have not given 70% whether it is percentage by mass or percentage by volume, but from the question itself we need to recognize it, we need to figure it out that it is percentage by mass, because throughout the question we need to calculate the mass of the nitric acid solution. Now students, this type of problem, it is not a direct problem. It is called preparing one solution from another solution, or sometimes we also call it a stock solution problem. See, in this case, what's the question? Question is, we have a solution of nitric acid, which is called here concentrated nitric acid solution. Now, for this concentrated nitric acid solution, it is given that it is 70% by mass. It is 70% by mass. Now, from this solution, we have to take some amount. We have to take some amount and put it in another container, right? And in this container, we have to make this solution whose volume is 250 ml, whose volume is 250 ml, and molarity is 2. Molarity is 2. So from this solution, take some amount, put it in another container, and in that container, you have to prepare this solution. Now, in this type of problem, the logic is, the main logic is amount of solute. Amount of solute. Whatever amount of this concentrated nitric acid solution you will pick, so in this, whatever amount of nitric acid is present, the same amount of nitric acid should be there in this solution which you are preparing. So what you can do the reverse calculation here. Because for the prepared solution which you have already prepared, the volume and molarity is given. So from volume and molarity, you can easily calculate the amount of solute in the prepared solution, right? Because molarity is 2, volume is 250 ml, we can say that here in this solution, number of moles of solute will be molarity into volume in liter. So 2 into 250 upon 1000. If you do the calculation, it will be cancelled by 4 times, it will be cancelled by 2 times, 1 upon 2, it will come out 0.5. So that means what? The solution which I have prepared, it contains 0.5 mole of solute. And my solute is what? HNO3. So from this, I can easily find out the mass of HNO3. If HNO3 is 0.5 mole, then the mass of HNO3 will be number of mole 0.5 into molar mass. And if you calculate molar mass of HNO3, so hydrogen's mass is 1, nitrogen's mass is 14, and for 3 oxygen, 16 into 3, 48. So 48 plus 14 plus 1, it will come out 62 plus 1, 63. Correct? So 0.5 into 63, that means what? 31.5 gram. So 31.5 gram of HNO3 is present in this solution which we have prepared. So now the point is, we need to take that much amount of concentrated nitric acid solution which contains 31.5 gram of HNO3. So here calculation can be done using unitary method. You can say what? Because this solution is 70% by mass, so if I have to take 70 gram of HNO3, so for 70 gram of HNO3, I need to take 100 gram of solution. This information is already given. So if I have to take 1 gram of HNO3, for that I require 100 upon 70 gram of this concentrated nitric acid solution. But my requirement is 31.5 gram. So for 31.5 gram of HNO3 students, I will require 100 upon 70 into 31.5 gram of concentrated nitric acid solution. And if you do the calculation, here terms will be cancelled. 31.5 into 100 is 3150 upon 70. That means 315 upon 7. And 315 upon 7, if you cancel it out, 7 fours are 28, 3 5, 7 5s are. So we will require 45 gram of this concentrated nitric acid solution. So answer should be C here. But I hope you have understood how we do this type of problem, where from one solution we have to prepare another solution. The logic is amount of solute. In this solution, whatever amount of solute is present, the same amount of solute we need to take from this, right? So keep practicing, because practice will make you perfect. Of course, the answer of this question is 45 gram of HNO3, and this question came in our NEET examination in 2013, right? And if you want to do more and more practice, then please get your DPP, right? We have already provided in the description and at PW app. So use that facility, all of you. Practice more and more problems, especially from the concentration term if you want revision. The first part within the solution chapter, which I told you earlier that we have 3 parts in the chapter: gas liquid solution, liquid liquid solution, and solid liquid solution. Right? The first part will be gas in liquid solution. That means your solute is in gaseous phase while your solvent is in liquid phase. So now students, the very first thing is, when you talk about gas liquid solution, you know what? It is always difficult to dissolve gases in liquid. Why? Because you know that gaseous state, a particle present in gaseous state, it will have very, very high amount of kinetic energy. Their interparticle separation will be also high. Their intermolecular force will be also very, very low. So because they are already very much separated, it is very difficult to keep them in the solution. Because they have very, very high kinetic energy, it is very difficult to keep them constantly inside a medium. So what we need to do here, we need to first focus on what can be the factors, what will be the factors on which solubility of gas depends, right? Because from those factors, we can control how much amount of gas can be dissolved in a liquid, Now, the very first factor is temperature, and this temperature part is very easy to understand. Students, I hope you can guess it easily. What will happen if I increase or decrease temperature on the solubility of gas? The point is very simple. For a gas, if you increase temperature, the solubility of gas will decrease. The solubility of gas will decrease. Now, please do not get confused here by the solubility of solids, because in case of solids, when you increase temperature, there is a possibility of increment in the solubility. But here we are not talking about solubility of solid, students, we are talking about solubility of gases. So for gases, whenever you increase temperature, the solubility of gas in liquid will decrease. Why? Because gases have already very high kinetic energy. And again, if you increase temperature, they will possess more and more kinetic energy. So they will have tendency to escape the solution. Like suppose, for example, I have a container. In this container, I have taken a liquid, and in this liquid, I have dissolved certain gas like oxygen, nitrogen, or any gas. So in the solution, I will have the gaseous particles, the gaseous molecules. When I will increase temperature, these particles will have more and more kinetic energy. So they will have more movement, more motion. So more movement means what? They will try to escape the liquid. They will try to go out from the liquid. And that's why their solubility will decrease. So please always remember that by increasing temperature, the solubility of gas decreases. Now, after temperature, the second factor on which solubility of gas depends is nature of gas and of course nature of solvent. You know what? We have a term here in the solution chapter. You will see that in the solid liquid solution part also. Like dissolves like, and it always follows. Like dissolves like means what? If you have a polar solvent, so that can dissolve polar solute easily. If you have non-polar solvent, so that can dissolve non-polar solute easily. Now here, in the gaseous topic, in the gas liquid topic, most of the time we do not talk about solvent, but please always remember that here our default solvent is water. Even I will not be mentioning again and again that what is my solvent. Solvent is default, right? And that is water in the gas liquid solution. Correct? So if I am using a water as a solvent, water is a polar molecule. That means what? In polar molecule, more polar gases will be definitely more soluble. Like dissolves like, always remember that. Now, after solvent, if you talk about nature of gas, so all of you please tell me in the comment box if you know, when we say that some parameter depends on nature, so what is the exact meaning of that? See, it's not only in the solution chapter, it's not only about the solubility. In your physics chemistry, at many places you say that this is the parameter and it depends on nature. Like resistivity in physics. Resistivity depends on nature of material. So what do we mean by saying nature of material, nature of gas? Right? If you know, please write down in the comment box, because now I will tell you. Okay. Nature of material or nature of gas, if any parameter depends on that, it means simply that for different material, the parameter will differ. For different material, the parameter will be different. That's the meaning, students. If I am saying that solubility depends on nature of gas, it means different gases will have different solubilities. Nature of gas, dependency of solubility means what? Different gases will have different solubilities. And of course, if you are doing the comparison, you need to do at a constant temperature. At a constant temperature, right? So at a constant temperature, if you take different gases, like suppose I am taking oxygen, I am taking hydrogen, I am taking ammonia. So I have taken 3 different gases. Now, definitely these 3 gases at a fixed temperature, they will not have the same solubilities, right? And if I am saying that they will not have the same solubilities, it means what? It means some of them will be more soluble and some of them will be less soluble. Like in these 3 examples, the most soluble gas in water is ammonia. The second most soluble gas is oxygen, and the third one is what? Hydrogen. Now from this, you will be getting questions in your exam. Like they can give you in the question 4 or 5 gases and they can ask which which gas is more soluble in water, which gas is less soluble in water, or what will be the order of solubility of the following gases. So those types of questions you will be getting from this topic. I have a suggestion for all of you. Whenever you study any subject, any topic, also focus on that part from any topic. What are the things from which you can get question? Because see, in chemistry even there are lots of topics which you study, which you find it interesting, but from that topic you won't get any question. So always while studying, focus on this, what type of questions we can get in the exam. Like from this part, you will be getting questions of comparison. Comparison of what? Solubility of gases. Right? Solubility of gases. Now, because by default here we are talking about water as solvent. So when you compare solubility of gases, you can compare it by 2 factors. Your first factor will be polarity. I hope that you all know regarding polarity from your chemical bonding chapter itself. In chemical bonding, you talk about all the dipole moment part and all. According to dipole moment, you decide whether a molecule is polar or non-polar. So here point is, if a gas is polar, so it will be more soluble in water as compared to non-polar gases. Like in this case, in this comparison, you noticed H2O2, these two are non-polar molecules. But NH3, it's a polar molecule. And that's the reason NH3 has more solubility in water. So you can compare on the basis of polarity, and if polarity is same, like suppose in this case, both H2O2, both are non-polar. So here you can't compare on the basis of polarity. So if polarity is not usable or both the molecule have same polarity, then you can compare on the basis of size. Then you can compare on the basis of size, because you know larger the molecule, larger the size of molecule, more is the van der Waals force, right? And more is the van der Waals force means more is the polarity. So out of H2O2, you know that O2 has larger size, and that's the reason O2 is more soluble in H2, correct? But please always remember in this solubility part, correct, we have a very small exception here. If you try to compare, theoretically, if you try to compare hydrogen and nitrogen, so according to polarity, both are non-polar. According to size, if you see, nitrogen is bigger than hydrogen. But solubility of students, hydrogen is more than nitrogen. Please remember that, please note it down. The reason is, in N2, we have triple bond. We have multiple pi bond. So that's why N2 has almost inert nature. And due to inert nature, nitrogen has low solubility also. Correct? So keep in mind regarding H2N2. Apart from H2N2, you can compare from these 2 factors, polarity and size. More polar gases are more soluble, or larger sized molecules, right, will be more soluble. Now, after talking about the nature of gas and how it affects your solubility and what type of question you will be getting in your exam, let's talk about the next factor, which is pressure. You know, for gaseous state, pressure is always important, because if you increase pressure, gases can be compressed. If you decrease pressure, gases will expand. And I think from this logic of compression expansion, you can easily figure it out. What will happen, what will be the effect of pressure on solubility of gas? Students, if I increase pressure, what will happen? Gases will be compressed. The interparticle separation will become less, right? So in a particular volume of solution, you can have more number of particle of gases. So eventually your solubility will increase. So by increasing temperature, solubility decreases. But when you increase pressure, with that, the solubility of gas will increase. The solubility of gas will increase. So we are done with the pressure. We have understood that pressure is directly proportional to solubility of gas. But for this particular factor, that is pressure, we have a law here. You can say that this relation between pressure and solubility, we have extended this topic a little bit further. Why? Why? To frame more and more questions for you, right, in the examination. So we have extended this topic, right? And in the pressure part, in the pressures factor part, we have a law which is called Henry's law. Eventually, Henry's law will tell you that how pressure affects the solubility. But we have to discuss the Henry's law. Now, first of all, what is the meaning of law? I told you already. It tells you regarding the relationship between pressure and solubility. The pressure is directly proportional to solubility of the gas in liquid. But if you talk about the definition part, the statement part, so you can define it as the amount of gas dissolved in a liquid at certain temperature will be proportional to or directly proportional to partial pressure of the gas. Partial pressure of the gas. Right? So the amount of gas dissolved indirectly is solubility, right? More amount dissolved means more solubility. So amount of gas dissolved in a liquid at a certain temperature is directly proportional to the partial pressure. Means at what pressure you are dissolving the gas. If you want mathematically, you can write this Henry's law as pressure proportional to chi. Now students, please focus here. In this case, in Henry's law, the solubility or the amount represented in terms of the concentration term mole fraction, right? So in this case, amount or solubility we are representing in terms of mole fraction, because see, more the gas dissolved, more the amount of gas dissolved, more will be the mole fraction of the gas, right? And pressure is directly proportional to amount or mole fraction of the gas. Now, you know, when you remove the proportionality constant, you will be getting some constant here, right? And that constant here is nothing but Kh, which is called Henry's constant. The law is what? Henry's law. So in Henry's law, the constant we are getting, it is named as Henry's constant. Kh is called Henry's constant. And this formula you need to write down and you need to remember, because see, from this Henry's law, pressure equals to Henry's constant into mole fraction. If you get a numerical question, believe me, that will be too easy for you. See what they can ask here. They can give you the partial pressure Kh, they can ask the mole fraction, or they can give you the Henry's constant, mole fraction, they can ask the partial pressure. So out of these three terms, one of the term will be unknown and two terms will be given, and that type of question you will be getting, right? Now, one more thing is there. Can you people tell me what will be the unit of Henry's constant according to principle of homogeneity? See, mole fraction is unitless. Pressure can have a unit of bar, atm, millimeter of Hg. So point is this, whatever unit of pressure is there, the same unit you will be having for the Henry's constant. So if I take pressure in atm, so Kh or Henry's constant, it will also have unit of what? Atm or bar or millimeter of Hg or torr, correct? So I hope that you have understood Henry's law, pressure equals to Henry's constant into mole fraction, and you have understood that Henry's law tells you that pressure is directly proportional to solubility of gas. So let us see the graph of Henry's law. You know what, students? At many places in chemistry, we talk about graph, right? But graph gives you the same information that you have already got from the formula. Like in Henry's law, we have a graph, we have to plot a graph, right? But that graph will also give you the same information. Same information means if you increase pressure, the solubility will increase. Like suppose we have pressure, we have KH, we have mole fraction. If I plot a graph between pressure and mole fraction. So what I am doing, I am plotting partial pressure on the y-axis and I am plotting mole fraction on the x-axis. Now if I try to get a graph here, you can draw the graph always by comparing with the general mathematical equations of certain curves. See, whenever you are plotting graph in chemistry, at least remember two graph or formulas of two graph. One is a straight line and one is rectangular hyperbola. The general equation of a straight line is y equals to mx plus c, and the general equation of rectangular hyperbola is x into y equals to constant. At least these two general equations, if you remember, you will be able to plot so many graphs in chemistry. Like here, pressure equals to kH into mole fraction. If you compare, it is quite similar to y equals to mx plus c, because I have kept pressure on the y-axis, I have kept mole fraction on the x-axis. So here I can say that kH is my slope and nothing is there, I can write 0. So 0 is my intercept, right? So intercept 0 means what? I will have to draw here a straight line, but that straight line should pass from the origin 0. And here slope is kh, which is positive, so it will have a positive slope. Positive slope means, just remember, positive slope means it will go upward. Negative slope means it will go downward. Up, down. Positive, up. Negative, down. That much is enough for you in chemistry. In this case, if this pressure equals to kh into chi, this equation has a positive slope, that means the graph will be something like this. Straight line with positive slope, cutting at 0, the y-axis, and here you can write that slope will be nothing but kh. Slope will be nothing but kh. So this is the graph of Henry's law, or this is the graphical representation of Henry's law. I hope that not only Henry's law, using the graph general equation of straight line and rectangular hyperbola, you can draw many graphs in chemistry. Just compare that our equation, it is similar to whether equation of a straight line or equation of rectangular hyperbola. Now, after this Henry's law, its graphical representation, we have to focus a little bit on the Henry's constant part, because in your examination, sometimes you will be getting question about comparison of Henry's constant. Comparison of Henry's constant. Now, what we have a data of Henry's constant in this. Please keep in mind, you don't have to memorize this data. We have this just for a comparison. You don't have to mug up the data part. In the questions, they will give you the data. So if you notice, at 293 Kelvin, we have to compare at same temperature. The Henry's constant of helium is 145 nearly. For hydrogen, it is 69.16. For nitrogen, 76.48. And for oxygen, it is 34.86. Now, just now, you have compared solubility of gases. And even I took the same example, right? I took examples of O2, H2, N2. So then you saw that out of O2, O2 is more soluble. And if you compare the KH values, for O2, KH is 35, and for H2, KH is almost 69. So definitely H2 has larger value of KH. So this tells us that solubility is inversely proportional to KH. Solubility of gas is inversely proportional to the value of KH at constant temperature. So you already know how to compare solubility of gas. So from that logic, you can compare KH value, Henry's constant value. So from today onwards, whenever someone asks you regarding comparison of KH, you first do the comparison of solubility, and reverse of that will be the order of KH. More soluble gases will have lower value of KH, and less soluble gases will have higher value of KH. Always remember that. And you will be getting questions from both solubility of gas and comparison of KH also. So now I hope you have understood Henry's constant and how we can compare Henry's constant. So let's see one of the questions related to Henry's constant and Henry's law. Can you do it, all of you? Take your pen paper again. Try to do it first by your own. Always try questions by your own first of all. You should have self-dependency in you, always. Self-dependency is the biggest thing we can have in our life. So, question is, Henry's law, constant KH for three different gases is given. A, B, C. These are the gases. For gas A, the Henry's constant is 145. Very good. For gas B, the Henry's constant is 2 into 10 to the power minus 5. Nice. Now for gas C, the Henry's constant is 35 and all have same unit, I guess. Yes, kilobar respectively. The solubility of these gases in water. So what an easy question we have. KH values are given and we have to compare the solubility. You know we have a reverse relation here. The gas which has lowest value of KH will be the most soluble one. So here lowest value of KH is 2 into 10 power minus 5 for B. So that means B will be the most soluble gas. And out of A and C, if you notice, C has smaller value of KH. So C will be the next most soluble gas, and here least soluble gas will be A. See, the order of solubility will be B, C, A. But the order of KH is A, C, B. And if you look at the answer, definitely it will be B, C, A. But students, again, this easy question came in our NEET 2024 examination. Correct? So that's what I was telling you. You will be getting questions of comparison of solubility as well as KH. Correct? Now, quickly, let's talk about another question from the same Henry's constant value. Can you do it? At least now by your own. KH values or Henry constant values of certain gases are given here. Same question, same type of question. For these gases, KH is given and you have to compare the solubility. Just look at the values. Which one is larger, which one is smaller. Right? If you notice, 40.3, 1.6, 1.8 into 10 power minus 5.413. So definitely here, the smallest value of KH is this one, 1.83 into 10 power minus 5. 1.83 into 10 power minus 5. So because KH is lowest for formaldehyde HCHO, this will be the most soluble gas, HCHO. Now the second smallest value is 0.413 and this is for methane gas. So methane will be on second place. Then it is 1.67 for carbon dioxide. So carbon dioxide will be at third place, and at last we will have argon. Right? More KH, low solubility. So in this case, answer will be formaldehyde, methane, carbon dioxide and argon. And that is your answer. Formaldehyde, methane, carbon dioxide and argon. And this question again, the same type of question which you got in 2024, we also had in the 2022 NEET examination. Correct? So you know, although these topics are easy, but they are important. You get questions from this in your examination. So now students, after the gas liquid solution, let's go into the second part of the chapter. We are done with the first part, which is gas in liquid solution. Of course, apart from that, we have talked about concentration terms, which is the prerequisite. But now let's move into the second part of the chapter and let's talk about liquid solution. Students, in the liquid solution part, whatever topic you are going to discuss, whatever questions you are going to solve, always remember inside that the most important point will be your vapor pressure. So here first thing is, try to understand what is vapor pressure of a liquid, of a mixture, how we calculate vapor pressure of any liquid. And after that you can go into the next topic, next part of liquid. Students, vapor pressure of any liquid is overall pressure applied by the vapor in equilibrium state. Right? If you try to define what is vapor pressure, so vapor pressure is pressure applied by the vapors in equilibrium state. Now, let me tell you how we calculate vapor pressure or how we can understand vapor pressure. Suppose that in a container, I have taken certain liquid and currently we have only liquid in this container. The upper part is empty here. Nothing is present. Only liquid is there. Now, if you start heating the liquid, and suppose at a constant temperature T Kelvin, right, I have heated the liquid. What will happen? Slowly, the particles or the molecules from liquid state, it will escape the liquid phase and it will go outside and they will create your vapor. Right? So at a constant temperature T Kelvin, if I am heating this liquid, slowly the molecules from liquid state, it will go into the vapor phase or they will form vapor one by one. First molecule, second molecule, third molecule and so on. Ultimately, after certain time, you will notice that in your container, at the same temperature, you have certain molecules in the liquid phase, but again, you have few molecules in the vapor phase now, right? And when equilibrium will be established at a constant temperature, so equilibrium means what? Equilibrium means now further no molecule from liquid will go into vapor phase. Or overall, you know from class 11th itself in your chemical or ionic equilibrium, that if equilibrium is established, then rate of forward is equals to rate of backward. So in this case, in case of vaporization, in case of vapor formation, what you can say that when equilibrium is established here, so in that case, rate of vaporization will be equals to rate of condensation. Right? So the rate in which the liquid molecule converting into vapor molecule, by the same rate, now vapor particles are condensing into the liquid phase. So at equilibrium, the number of particles in vapor phase and the number of particles in liquid phase will remain constant. Now, at this instant, at this state, all these vapors we have, they will apply pressure on the container, on the liquid surface, right? And this pressure applied by the vapors is known as vapor pressure. So, it is easy to understand, no doubt in that. Once you have understood it, you will never forget it throughout your life. But this particular term, this particular vapor pressure term is important for us in the liquid-liquid solution, right? So always try to understand this, that in equilibrium, we have equilibrium between liquid phase, vapor phase, and here whatever pressure is applied by the vapors, right, in 360 degree on the container, on the liquid, that pressure is called as what? Vapor pressure. And also remember few points. Your vapor pressure is temperature dependent. Correct? Like here I kept my temperature T Kelvin. So suppose at T Kelvin, I got vapor pressure P1. Now, if I start heating the liquid and again, if I heat the liquid further, if I increase the temperature further from T Kelvin to T plus 10 Kelvin, T plus 20 Kelvin, so by increasing temperature, more vapor will be created. And when more vapor will be created, your vapor pressure will increase. So by the increase in temperature, automatically the vapor pressure will also increase, right? So we have to always measure vapor pressure at a constant temperature. And normally we do at the boiling point. Normally we do measure the vapor pressure, standard vapor pressure at the boiling point. Correct? Now, after understanding what is vapor pressure of an liquid, let's talk about the very first point and you can say most important point in the liquid-liquid solution part, which is Raoult's law. Students, first of all, let me tell you that Raoult's law is about mixture of liquids. Suppose you have taken a liquid A and you have mixed a liquid B. So liquid A, liquid B, when you mix it, ultimately you will get a solution of A and B. Solution of A and B. Now try to understand this a little bit on the molecular level also, because that will help you. See, when I take liquid A or when I take pure liquid A, so inside the container, when I will be taking pure liquid A, so I will be having only molecules of A in it. When it is pure A, it will contains only pure A molecules. Similarly, when liquid B is in pure state, so that will have only the molecules of B because they are pure, obviously. Now, when you will mix them, so in the mixture of A and B, together in the liquid part, you will have particles of A as well as particles of B. So in the mixture, obviously, you will have particles of liquid A and you will have particles of liquid B. So here I was just explaining that what is the meaning of pure liquid and what is the meaning of mixture. Pure liquid has only one type of particle, mixture has more than one type of particle. Here, two type of particle, A and B. Now, point is this, when it comes to vapor pressure, so vapor pressure can be calculated for the pure state and for the mixture, both. Like here, suppose if I want vapor pressure of pure liquid A, what I will do? I will heat liquid A, right, at boiling point. I will get some vapor, equilibrium will be established, and when equilibrium will be established, the amount of vapor will be constant, and there whatever pressure is there, so that will be the vapor pressure of pure liquid A, and let me call it P naught A. P naught A signifies here vapor pressure of pure liquid A. Similarly, if I want, I can calculate vapor pressure of pure B. Suppose if I heat this B at its boiling point again, and vapor will start forming. After certain time, equilibrium will establish. So when equilibrium will be established, so then amount of vapor will remain constant, and there whatever pressure is applied by the vapors of B, that I can say is P naught B, and here P naught B is nothing but vapor pressure of pure liquid B. Now just like these pure liquids, what you can do, you can find vapor pressure of this mixture. You can find vapor pressure of this mixture. If you heat this mixture of A and B, and if both are volatile, volatile means both can be vaporized easily. So if both A and B are volatile, what will happen? Particles of A will go from liquid state to vapor state, and particles of B will also go from liquid state to vapor state. Fine. So in the vapor phase, you will have particles of A as well as particles of B. Now here, you can say that they can have individual pressure. Like in this mixture, in the vapor phase, whatever particles of A we are getting, suppose they are applying pressure PA. So this will be vapor pressure of liquid A. And B particles, if they are applying pressure PB, so PB is the pressure of B. Correct? So just like pure liquid, we can obtain vapor pressure in case of mixture also for the volatile particles, right? And once in the mixture, equilibrium is established, what will happen? In a closed container, of course the container should be closed here, right? In a closed container, when equilibrium will be established, you will notice you will have liquid phase as well as you will have vapor phase. right? The particles of A and B, here I am indicating green particle as A and red particle as B. So particles of A and B will be in liquid phase also, and particles of A and B will be in your vapor phase also. Pressure of A will be PA and pressure of B will be what? PB. Now coming back to Raoult's law. Raoult's law tells you regarding these vapor pressures of A and B. It tells us that these vapor pressures of A and B will be proportional to the mole fraction of A and B that we have taken in the liquid phase. So basically, in liquid phase, if mole fraction of A is high, so that means A will have more vapor pressure. Or if mole fraction of B is high, then we will have more vapor pressure of B. That is your Raoult's law. So let's write down the definition of Raoult's law, what it explains, what it says. It says that vapor pressure of any component in liquid mixture is proportional to mole fraction in liquid state. Please focus on this point. What we are saying that vapor pressure of any component, whether it is A or B, it is proportional to mole fraction, but mole fraction of which state, which phase? Liquid phase, right? Like here in the diagram you can notice that when equilibrium is established, we have particles of A in the vapor phase also, and we have particles of AB and in liquid phase also. So in liquid phase, whatever number of A particle, B particles are there, so here in the liquid phase itself, if you calculate mole fraction of A and let us say it is chi A. In the same liquid phase, if I calculate mole fraction of B, let us say it is chi B. And here the vapor pressure of A and B, let us assume that it is PA and PB. Correct? So according to Raoult's law, the vapor pressure of A will be proportional to mole fraction of A in the liquid phase, and vapor pressure of B will be proportional to mole fraction of B in the liquid phase. Students, that's the meaning of Raoult's law. That's the definition of Raoult's law. And if I write it mathematically here now, from that example, from that diagram, I can say vapor pressure of A proportional to chi A, and at the same time vapor pressure of B is proportional to chi B. And here when you remove the proportionality constant, students, you get constant as pure vapor pressure. If I remove this proportionality constant in this case, so vapor pressure of A in solution will be equals to P naught of A into chi A. Here P naught A is vapor pressure of pure liquid A. You know how you can justify it? Suppose when you take liquid A in the pure state, no B is there, right? So in pure state, automatically chi A will be 1. So when chi A is 1, when it is pure liquid, the vapor pressure should be equals to P naught A. And similarly, if you talk about here also if you remove the proportionality constant, so vapor pressure of B in the solution will be equals to vapor pressure of B in the pure state multiplied by mole fraction of B in the liquid phase. So students, please note it down, because you get a lot number of numericals, a huge number of numericals from this. A very simple Raoult's law. PA equals to P naught A chi A and PB equals to P naught B chi B, right? So after understanding the definition and mathematical expression of Raoult's law, let's talk about its graph. Just like Henry's law, in case of Raoult's law also, we have to sketch a graph here. But you know how we sketch graph in chemistry, right? Just by remembering the general equations of a straight line and rectangular hyperbola, right? In case of Raoult's law, if you notice, for the first component A, for liquid A, inside the mixture, I can say that PA will be equals to P naught A chi A. Now students, just focus here. If I plot a graph here, on the y-axis, I will keep vapor pressure of A, and on the x-axis, I will keep vapor mole fraction of A. So here mole fraction of A is 0 and here mole fraction of A is 1. Now if you notice, PA equals to P naught A chi A, it is something similar to y equals to mx plus c. It is something similar to y equals to mx plus c where c is 0. And if you compare, I have plotted vapor pressure of A on the y-axis, I have plotted chi A or mole fraction on the x-axis. So in this case, P naught A will be your slope. P naught A will be your slope. And definitely because it is PA equals to P naught A chi A, because it is similar to y equals to mx, which is the equation of a straight line. So plot of this will also follow straight line. It should be something like this, straight line. And if you want, you can match this graph, you can relate this graph from the expression itself. When chi A is 0, so P naught A into 0 should be 0. So PA will be 0 here. When chi A is 1, so P naught A into chi A is P naught A. So when chi A is 1, so at this point, the value of PA should be equals to what? P naught A. So this is the curve, this is the graph according to Raoult's law for the vapor pressure of A. Vapor pressure of A. Now see, for liquid B, for the second component, if you want, you can plot a different graph. But what we have done here, because we have a relation between the mole fraction, you know that chi A plus chi B will be equals to 1. So from this knowledge, what we can do, we can plot the graph of vapor pressure of second component in this graph only, in this graph itself. Because the point where mole fraction of A is 1, at the same point, if you notice, mole fraction of B will become 0. And the point where mole fraction of A is 0, at that point, the mole fraction of B will become 1. So in the reverse order, in this only, you can plot graph of vapor pressure of B. Basically at this point now, with respect to the component B, chi B is 0. Chi B is 0. So here vapor pressure of B will be 0. At this point, chi B is 1. So at this point, PB will be equals to what? P naught B. So here the graph of PB will look like this. At this point it will be equals to P naught B. And this is the graph of PB. Correct? So in the same graph, we can plot vapor pressure of A and vapor pressure of B according to Raoult's law. And both the curve will be straight line because this equation itself follows y equals to mx. Correct? Later on you will see that if you want, you can calculate the total pressure also. Total pressure means pressure of A and B both. And if you try to plot a graph for the total pressure, so total pressure graph will be the line joining the point P naught A and P naught B. This will be the graph of total pressure. But right now you can understand, I hope you have understood the graph of PA and PB. So after the graph part of PA PB, now let's talk about a thing from class 11th, but we need that here in the solution chapter. Students, in your gaseous state chapter or in your thermodynamics chapter, you must have seen, you must have heard somewhere that we have a law called Dalton's law or Dalton's law of partial pressure. Now, what we need to do here, we have to apply that Dalton's law. Dalton's law is applicable for gases, but what we can do, we can apply Dalton's law for vapors also. So remember that liquid vapor equilibrium for pure or for mixture. Here we are talking about solution or mixture. So again, once again, if you talk about liquid vapor equilibrium in a solution, so again, in the liquid phase, you have particles of A, particles of B. In the vapor phase, you have particles of A, particles of B. So now, if you are interested in Dalton's law, you have to focus only on the vapor part. Please remember that in your mind. If you want to discuss Dalton's law here, just forget about the liquid phase, because Dalton's law has nothing to do with the liquid phase. Dalton's law is applicable only in this vapor part, only in this vapor part. So in this vapor part, suppose I told you already that vapor pressure of A we have taken PA and vapor pressure of B we have taken PB. Now Dalton's law says that if you calculate the total pressure, so total pressure will be simply algebraic sum of the individual pressure. So in the vapor phase, if I want the total pressure of the total vapor, so total pressure will be equals to PA plus PB. And please keep in mind that this relation PT equals to PA plus PB, we are writing it from Dalton's law, not Raoult's law. Although you can use Raoult's law here. How? I told you total pressure is PA plus PB. Now according to Raoult's law, you can substitute PA as P naught A chi A, and you can substitute PB as a P naught B chi B. Now this is a very important relation for us in this topic. You get so many questions from this. Total pressure equals to P naught A chi A plus P naught B chi B. But overall, this relation we have obtained using Dalton's law and Raoult's law. Also, in Dalton's law, we say that total pressure is equals to sum of individual partial pressure or vapor pressure. But in Dalton's law, we have one more point. And that point is, from the total pressure, you can calculate the individual pressure also. Like in the first case, in the first point, I was telling you can calculate total pressure from partial pressure. Just add the partial pressure, you get the total pressure. Now here the second point is, you can get the partial pressure from total pressure. How? Just by multiplying the mole fraction. Just by multiplying the mole fraction. So if I want, I can get vapor pressure of A by multiplying total pressure with mole fraction of A. Now please focus here, students. Please focus here. This mole fraction is from the vapor phase. It has nothing to do with the liquid phase. So this Ya is the mole fraction of A in the vapor phase. In the vapor phase. Right? But this chi A which you were using in the Raoult's law, this chi A was the mole fraction in the liquid phase. So what will happen here? You will be getting questions. There will be so many questions from Raoult's law, Dalton's law, in which they will give you mole fraction of liquid phase, they will ask mole fraction of vapor phase, or vice versa. They will give you mole fraction of vapor phase, or they will ask mole fraction of liquid phase. And the same thing you can apply for the second component. According to Dalton's law, if you want vapor pressure of B, so that can be equals to total pressure into mole fraction of B. But please always remember, and even if you want, you can note it down, that here Ya and Yb, these are the mole fractions not in liquid phase but in vapor phase. In vapor phase. Correct? So if you want to solve numericals from this topic, from this Raoult's law, just remember these three four formulas. Pa equals to P naught A chi A, Pb equals to P naught B chi B, Raoult's law. Pt equals to Pa plus Pb, Dalton's law. Pt equals to P naught A chi A plus P naught B chi B, Dalton's law plus Raoult's law. Pa equals to Pt into Ya, Pb equals to Pt into Yb, Dalton's law. Just these 3-4 formulas and you are done with all the questions of Raoult's law. So, take your pen paper and brain again, use it and try to solve this question with me. Correct? And if you want, you can pause it again and you can do it by your own. Otherwise, do it with me, because this is the first question from Raoult's law. So, here, first thing is, do not rush into the solving the problem. Before doing it, first always read the question carefully, because many times what students do, they do mistake in reading the question. So that's a kind of blunder it is. Don't do blunders here. Read the question carefully first, then only go for the solution. So question says the vapor pressure of two liquid P and Q. So we have two liquid P and one is Q are 80 and 60 torr respectively. So these are the vapor pressure of two liquids. So definitely it should be in pure state, right? So that means what? P naught of P is 80 and P naught of Q is 60. So for P and Q, the vapor pressure in the pure state they have given 80-60. Now, the total vapor pressure of solution obtained by mixing 3 moles of P and 2 moles of Q. Now, if I take 3 moles of P and I mix it with 2 moles of Q, I have to find out the total pressure. So, total pressure you can directly apply this formula. P total equals to P naught A chi A plus P naught B chi B. Now, P naught A is given. Okay, in this case, we don't have A and B, so let me reverse it for you. So we should not have any confusion. P total here will be P naught of P into mole fraction of P plus P naught of Q into mole fraction of Q. Now, for P, the pure vapor pressure is 80. So 80 into mole fraction, I think you can find, right? If it is 3 mole, 2 mole, total mole will be 5. So mole fraction of P will be moles of P 3 upon total moles 5. It will be 0.6. And mole fraction of Q, if you calculate, so you can do it by 2 upon 5, but you can also do it by 1 minus 0.6. 1 minus 0.6 because summation of mole fraction should be 1. So mole fraction of P is 0.6, mole fraction of Q is 0.4. Now just substitute the values. Mole fraction of P, I will put 0.6 plus vapor pressure of pure Q, which is 60, into mole fraction of Q, which is 0.4. Just multiply 0.6 into 0.6 into 8, 48 plus 60 into 0.4, 0 into 0.4, 4, 24. 8, 4, 12, 2, 4, 2, 6 plus 1, 7. This will come out how much? 72 torr. So it's a very, very direct question we have. Pure vapor pressures are given, moles are given or mole fractions are given and we have to find total pressure. So definitely here the answer should be A, that means 72 torr. Yes, it is 72 torr. And this question is a PYQ. It came in very old, AIPMT 2005, but believe me, this type of question you get these days also in the NEET examination. Correct? So now I think you have understood what type of problem you will be getting in the Raoult's law. So the next question now you have to do. You have to do it, all of you, because it's a exactly similar type of question we have. Same type of question. The correct option for the value of vapor pressure of a solution at 45 degree. See, when you say vapor pressure of solution, so this means basically the total pressure. This means total pressure. So we have to find total pressure and here we are mixing what? Benzene and octane. Their molar ratios are 3 and 2. Means 3 moles of benzene is mixed with 2 moles of octane in the ratio. And their pure vapor pressure is given 280 for benzene and 420 for octane. It's the same question, right? We have to apply that P total equals to P naught of, in this case, benzene, B. I am writing benzene as B here, into mole fraction of benzene plus octane I am writing as O. So P naught of O into mole fraction of octane. Just put the values. P naught of benzene is 280. So 280 into mole fraction of B or benzene will be, benzene is 3 mole. If total mole is 5, so 3 by 5 plus for octane pure vapor pressure is 420 and for octane mole fraction will be, if octane is 2 mole then total mole is 5, so 2 by 5. I hope you can do the rest calculation. It will be 280 into 0.6 plus 420 into 0.4, right? The rest of the calculation I hope you will do, because it's just a simple multiplication and addition. And if you calculate, your answer will be 336 mm of Hg here. And this question, the previous one was from AIPMT 2005, but this question we got in the NEET 2021, and both questions were nearly similar kind. So let's do more practice from this topic, because from Raoult's law, Dalton's law, you will be getting numerical problems only most of the time. Sometimes there will be logical problems, you will see that also. So can you do the next one? In water saturated air means what? We have a kind of mixture. We have a mixture of air with water, H2O. So in this air-water mixture, the mole fraction of water vapor is 0.02. So they are saying mole fraction of water is 0.02. Automatically, before reading the question further, what you can do here, you know that if air water is there, so the sum of mole fraction of both should be equals to 1. Now if mole fraction of water is 0.02, then mole fraction of air, in this case, you can say it will be 1 minus 0.02, which will be equals to 0.98. 0.98. So 0.98 is the mole fraction of air. Now read the question further. If the total pressure of the saturated air is 1.2 atm, so they are saying the mixture of air water, its total pressure is 1.2 atm, then what will be the partial pressure of dry air? Students, don't you feel that this question is a direct question from Dalton's law, where I told you that partial pressure will be equals to total pressure into mole fraction. Suppose if I have to calculate here the partial pressure of dry air, so dry air means what? Dry air means without water, right? So dry air will be total vapor pressure or total pressure, which is 1.2 atm, multiplied by the mole fraction of dry air, which is 0.98, right? If you do the calculation, 1.2 into 0.98, round off, it will come out 1.176 atm. So this question we got a direct question from Dalton's law of partial pressure. That partial pressure, of course, it is C, 1.176. And this question came in when? NEET 2019. So total pressure into mole fraction of gas equals to the partial pressure of gas. Now moving further, don't stop, keep solving, keep calculating. The next question we have from Raoult's law is PA, PB are vapor pressure of pure liquid components A and B respectively for a binary solution. If chi A represents the mole fraction of A, then total pressure of solution will be. So here we have to solve just the expression part. You don't have to do some numerical calculation in this. Point is, we know that if A and B are the components, so using Dalton's law, using Raoult's law, I can write total pressure as PA chi A plus PB chi B. Normally we write PA pure vapor pressure as P naught A and P naught B, but in this question they have said PA, PB are the pure vapor pressures of A and B. So what we have to do here, if you look at the options, we have to just eliminate a mole fraction of B from the expression. We have to find the total pressure in terms of mole fraction of A only. Now what can be done here? We can substitute mole fraction of B in terms of A from this relation. You know that chi A plus chi B is equals to 1. So from here I can write chi B, mole fraction of B, as 1 minus chi A. So if I substitute here, I will be getting PA chi A plus PB, and instead of chi B I can write 1 minus chi A. Now solve, you will get your answer. This is PA chi A plus PB into 1 PB, PB into minus chi A, so minus PB chi A, PB you take here, and from PA chi A minus PB chi B, if you take chi A common, so this will come out PA minus of PB. Now just see the option, in which case they are saying P total is PB plus chi A into PA minus PB. I think option D, right? PB plus chi A into PA minus PB. So that will be your answer. And this simple question just about the expression of total pressure from Raoult's law, Dalton's law, we got in the NEET 2012 examination. Correct? Now, finally, let's talk about a question which I was telling you that you get questions like where mole fraction of liquid phase is given, vapor phase you have to calculate, or vice versa. Please read this question first carefully, all of you. A solution has 1:4 mole ratio of pentane hexane. So in this case, we have pentane. Let me represent pentane here by P and hexane by H, just for representation. Now for pentane hexane, the molar ratio is 1:4. So from this, first of all, we can find the mole fraction. If it is 1 mole, then it is 4 mole, then total mole is 5, should be 5 in the ratio. So mole fraction of pentane will be 1 upon 5, which is 0.2, and mole fraction of hexane will be 4 upon 5, which is 0.8. So mole fraction of P, pentane 0.2, mole fraction of hexane 0.8. Now the vapor pressure of pure hydrocarbon at 20 degree is 440 mm and 120 mm for pentane and hexane respectively. The mole fraction of pentane in the vapor phase you have to calculate. Now, if you want mole fraction from the vapor phase, the first thing is use Dalton's law. Dalton's law for pentane, right? You can say that vapor pressure of pentane in the solution should be equals to total pressure into mole fraction of pentane in the vapor phase. This we are writing from Dalton's law. I hope you remember that, right? PA equals to PT into YA, PB equals to PT into YB. Now this term we have to calculate, the mole fraction of pentane in the vapor phase. So what I can say that mole fraction of pentane in the vapor phase will be equals to vapor pressure of pentane upon total vapor pressure. Now using Raoult's law, you can write these. Vapor pressure of pentane will be P naught of pentane into mole fraction of pentane in liquid phase upon P naught of pentane mole fraction of pentane plus P naught of hexane into mole fraction of hexane. Now just substitute the values, you will get your answer. P naught of pentane is given how much? 440. So 440 into mole fraction of pentane we have 0.2 divided by, again, pure vapor pressure of pentane 440 into mole fraction of pentane in liquid phase 0.2 plus pure vapor pressure of heptane, which is 120 into mole fraction of heptane in liquid phase 0.8. You can do the calculation and definitely you will be getting your answers, right? Just multiply and divide. Your answer will be 0.478 in this case, option D. And this question, students, again we got in the AIPMT 2005. So now I hope that you have understood how to calculate mole fraction in the vapor phase, and at least you have understood that these are two different mole fractions. One from liquid phase we use in Raoult's law, one from vapor phase we use in Dalton's law, right? And I hope you have noted down all the formulas of Dalton's law and Raoult's law. So now students, let's talk about the next topic that we have in the chapter, and this is again a topic from liquid in liquid solution. It is ideal and non-ideal solution. Students, here first thing that you should focus on is what is the difference between an ideal and non-ideal solution, right? So the first difference between ideal and non-ideal solution is, an ideal solution is that liquid solution which will obey Raoult's law. Raoult's law. So if a liquid mixture is there and it is obeying Raoult's law, then you can say that that particular solution will be ideal solution. But on the other hand, if there is a liquid solution and it is not following, it is not obeying your Raoult's law, then that solution, that liquid solution will be called as non-ideal solution. So this is one point regarding your ideal and non-ideal solution. Ideal solutions, they will obey Raoult's law, while non-ideal solution, they will not obey Raoult's law. Now, apart from that, there is a more difference between these two. There are more differences between the ideal and non-ideal solution, and we will see them one by one. See, students, please try to understand the difference between ideal and non-ideal solution on the basis of mixing, and during mixing, how their interparticle attraction, how their intermolecular force changes. See, if you have two liquids, let's suppose I have liquid A and I have another liquid B, right? And I am going to mix it. I am going to mix liquid A and liquid B to prepare a solution of A plus B. Now the point is, when you take liquid A in the pure state, so in the pure liquid A, you will have intermolecular force, or you will have attractions between the particles of A. Obviously, if you are taking the pure liquid, so in the pure liquid, you will have particles of only that liquid. In liquid A, I will be having particles of only A, molecules of only A. So in that case, the intermolecular force will be in between the molecules of A. Similarly, if I take liquid B in the pure state, so in the pure state, liquid B will have only the molecules of B, right? And in that case, there will be interparticle attraction, there will be intermolecular force between the molecules of B. So molecules of A, they have their own intermolecular force, molecules of B, they have their own intermolecular force. Now, the point is, when you will mix liquid A and liquid B, you will get a new type of attraction. When you will mix, you will get a new type of attraction. Now you will have attraction between particle A and particle B. This interaction of particle A, particle B will definitely, right, not there when they were in the pure state. But as soon as you mix them, then you will be getting a new attraction between molecules of A and molecules of B. Now the point is, if the intermolecular force between A and B, it is similar to the intermolecular force between B and B and A, so then it will be called as ideal solution. More precisely, I should say here that out of liquid A, liquid B, let's assume that liquid B is your solvent. Liquid B is your solvent. Then the comparison will be done between solvent and solution. So if liquid B is solvent here, I can say the interparticle attraction between B and B and the interparticle attraction between A and B, if they are similar, if they are same, then that particular solution will be called as ideal solution, right? But on the other side, if the new attraction that is forming between molecules A and B, it is different from the attraction of particles in the pure state, in the pure solvent, then that will be called as non-ideal solution. Now, here you can have two cases. Suppose that when I mixed liquid A and liquid B, and I got a new type of attraction between the particles of A and particles of B, and the attraction between particles of A and particles of B, if the intermolecular force between A and B, it is stronger. It is stronger as compared to what? As compared to the attraction that we had between the pure solvent. And here I have assumed solvent as B. So, if the attraction between AB particle, it is stronger than the BB particle, then it will be called as non-ideal solution. And one more case is there in which the solution will be called as non-ideal solution. Suppose, students, if the attraction between particle A and B, it is weaker, right? The intermolecular force of attraction between A and B, it is weaker as compared to the pure solvent. In that case also, the solution will be called as non-ideal solution. So, if AB attraction is same as BB attraction, it is ideal solution. If AB attraction is stronger or weaker as compared to the BB attraction or the attraction in the solvent particle, then in that case, the solution will be called as non-ideal solution. And from here onwards, what we do, we classify these two into two parts. One case where the new attraction is stronger, and other case where the new attraction is weaker. Now, when the new attraction is stronger, so that case is also known as, later on you will be seeing, as negative deviation from Raoult's law. I will tell you very soon that why in this case when your AB attraction is stronger, we are calling it negative deviation. But right now you can just write it down that when AB attraction is stronger, so that particular case of non-ideal solution, we call it as negative deviation and negative deviation from Raoult's law. Similarly, if you talk about AB attraction, which is weaker, so the weaker case is known as what? Positive deviation. Positive deviation from what? Positive deviation from Raoult's law, right? So ideal solution, it obeys Raoult's law, negative deviation from Raoult's law and positive deviation from Raoult's law, right? And I hope that you have understood the differences between the interparticle attraction in case of ideal and both the cases of non-ideal solution. Students, let me tell you, this intermolecular force point is the most important point here, right, regarding the ideal and non-ideal solution. Because you know what? You know that in your class 11th, you discussed about the chapter thermodynamics. So if you remember thermodynamics, there you must have studied several terms, several parameters like enthalpy, internal energy, entropy, Gibbs energy, work and all, heat. Now here in this ideal, non-ideal solution topic, what we have to do? We have to compare some of the thermodynamical parameters and they will be asked in your examination. Those thermodynamical comparisons will be asked in your NEET examination. And those comparisons can be easily done with help of the knowledge of interparticle attractions. Like here, the very first point is we have to compare what will be the changes in enthalpy in all the cases. Like when I am preparing an ideal solution, when I am preparing a non-ideal solution, so what will be my change in the enthalpy? So the very first point is when you come to ideal solution. So in case of ideal solution, what will happen? As soon as you mix liquid A and liquid B, as you prepare the solution, so for solution, for mixing, the delta H will be 0. That means when we prepare ideal solution, so delta H of mixing, delta H of dissolution will be 0 here. Why? If you want to understand that, just go back on the intermolecular force part again and try to understand this on the basis of thermodynamics. See, when you will be mixing liquid A, liquid B, what will happen? New attractions will be created, new types of bond will be created, and that bond will be between A and B. The new attraction will be created between A and B. And for the creation of attraction between particle A and B, some of the attractions of B and B will be dissociated, will be broken. Now, you know that whenever a bond is broken, so that absorbs heat. And whenever a new bond is formed, so during that energy or heat will be released. Now, what is the point here? When you break this BB bond, it will absorb certain amount of heat. And when this new AB bond will be created, certain amount of heat will be released here. Now, because the intermolecular forces between B and B and A and B, we are assuming same. So that means what? The amount of heat absorbed while breaking BB bond, right? And the amount of heat released while we are forming AB bond will be equal. So amount of heat absorbed is equals to amount of heat released. That means what? Overall heat transfer will be 0. And that's why we say in case of ideal solution, the delta H will be 0. Now, on the similar basis, you can understand about change in enthalpy, the value of the sign of delta H in case of non-ideal solution, whether it is negative deviation and positive deviation. But before I explain this on the basis of intermolecular force, first let me tell you that you can remember the sign of delta H on this point, negative and positive deviation. But please let me tell you one thing, that on the basis of delta H, we have not named these types. It is based on their vapor pressure. But just for memorizing purpose, you can do that. You can do what? You can remember the sign of delta H, correct? How? Because in case of negative deviation, the sign of delta H will be negative. Means what? When a negative deviation from Raoult law solution is prepared, so that case will be exothermic. In case of exothermic, delta H is negative. And when you have a positive deviation from Raoult's law, that type of mixture, right? So during the mixing process, your delta H will be positive. So I was telling that you can remember like this: negative deviation, in this case delta H negative, positive deviation, in this case delta H positive. Now let's understand why in these cases delta H is negative or positive, and it is again based on the interparticle attraction. See, if AB attraction is stronger, that means what? Stronger attraction is getting formed, and when stronger intermolecular force will be formed, that means in that case more heat will be released. Suppose that when the bond is getting formed between particle A, particle B, so in that case Q2 amount of heat is getting released. Again B and B, some of the B and B bonds will break, and during that suppose Q1 amount of heat is getting absorbed. Now because BB is weaker bond and AB is a stronger bond, right? So stronger bond means more heat, correct? So during the formation of AB, more amount of heat will be released here and the absorbed heat will be less. So because more amount is getting released, more heat is getting released, the net change will be, there will be a release of energy, there will be release of heat. And that's why in this case the process will be exothermic and sign of delta H will be negative. But on the other side, when your new attraction AB, it is weaker. So in that case, because weak bond is getting formed, in this case, suppose that if amount of heat released is Q2 and the amount of heat absorbed during the dissociation of BB bond is Q1. So here, BB bond is stronger as compared to AB, correct? So during the dissociation of BB bond, you will require more heat and less heat will be released during the formation of AB. So in this case, less heat is getting released and more heat is getting absorbed. So overall, net if you see, there will be absorption of heat, there will be absorption of energy. And that's why this particular mixing process will be endothermic in nature. And you know very well that for endothermic process, delta H sign is positive, right? So from today onwards, always remember that in case of ideal solution, delta H 0, in case of stronger attractions between solute solvent particle, delta H negative. In case of weaker attraction between the solute solvent particle, delta H is positive. Delta H positive is positive deviation, delta H negative is negative deviation. But once again, these names, negative, positive deviations, are not based on the sign of delta H, they are based on vapor pressure. Now, apart from delta H, we have to also compare one more parameter from thermodynamics, and that is change in volume. Right? If you calculate change in volume while preparing ideal solution, so change in volume will be 0 again in case of ideal solution. Again it is based on interparticle attraction, because interparticle attractions are same before mixing, after mixing, right? So they will acquire same space before mixing and after mixing. And if they are acquiring same space, that means they will have same volume before mixing, after mixing. That's why the change in volume is 0. And same concept can be applied here. Suppose that when AB attraction is stronger, so stronger attraction means in that case particles will become more and more close to each other, right? They will acquire lesser space. So in this case, as compared to pure solvent, the solution will have lesser volume. The volume will decrease. That's why in this case delta V will be negative. But on the other side, when the solute solvent attraction is weaker, correct? Weak attraction means what? These particles will have more separation. So in the solution, solute solvent will acquire more space, more volume as compared to pure solvent. So when your solution has more volume as compared to solvent, that means what? Your volume has increased. And if your volume has increased, that means in this case, delta V, change in volume, will be positive. So one more thing is there which can be easily remembered, that the sign of delta H, delta V, in each case, ideal, non-ideal solution, it is same, right? Now, there are two more parameters, but they are almost same in each cases. Apart from delta H, delta V, people will also ask that what is the change in Gibbs energy, delta G. So always remember that delta G will be negative because whenever you are mixing, so these mixing process, whether it is non-ideal, ideal solution, these mixings will be spontaneous, and for spontaneous processes delta G negative. So whether it is ideal, whether it is non-ideal, in both the cases the sign of delta G will be what? Negative. And one more thing is there which is common between ideal and non-ideal solution, and that is entropy change. If you calculate entropy change in any of the mixing process, so entropy change will be again positive, because whether it is ideal or non-ideal solution, the overall space or entropy will increase. The randomness of particle will definitely increase. So these two parameters have same sign whether it is ideal or non-ideal solution. And from these four parameters or their sign, you will be getting questions in your exam. Sign of delta H, delta V, delta G, delta S, in case of formation of ideal and non-ideal solution. So now I hope that you all have understood regarding the ideal, non-ideal solution and their differences, especially based on the intermolecular force, because each comparison is done on the basis of intermolecular force. So now students, as we have understood what is ideal, non-ideal solution, let's talk about a very important point which you need to note down, because you will forget it. So you need to revise it again and again. You know what? Those ideal, non-ideal solution just we discussed, for them we have to also remember some of the examples. Examples of ideal solution, examples of non-ideal, and in the non-ideal part, positive and negative deviation. Right? So take your pen paper and please note down these examples, because they are asked in the exam directly. They will directly ask, what is the example of ideal solution? Which of the following is an example of positive deviation from Raoult's law? Which of the following is an example of negative deviation from Raoult's law? Correct? So first of all, if you talk about ideal solution, so ideal solution perfectly cannot be prepared, right? But approx ideal solution you can say. Approx ideal solution you can get if you mix butyl bromide with butyl chloride, hexane with heptane, benzene with toluene, or chlorobenzene with bromobenzene. Now, if you notice all these examples, you will find something common here, and which will help you in order to memorize these examples. Students, if you know organic chemistry, you know that butyl bromide and butyl chloride both are alkyl halides, same type of functional groups. Correct? And if you talk about hexane heptane, both of them are alkanes. They are the compounds of same homologous series. If you talk about benzene toluene, again they are from the same homologous series, that means benzene, and difference between benzene toluene is only for CH2. And chlorobenzene, bromobenzene, again both of them are aryl halides, similar type of functional groups. So here what you can do, you can remember like this: if I have two compound from organic and they have same type of functional group, or they are from the same homologous series, correct, then that mixture will behave as ideal solution. Correct? On the other side, if you talk about non-ideal solution, so in non-ideal, in case of positive deviation, we have examples like methanol plus water, or ethanol plus water, or methanol plus carbon tetrachloride, or ethanol plus cyclohexane, acetone plus carbon disulfide, acetone plus ethanol. So these are some of the examples of positive deviation from Raoult's law in case of non-ideal solution. Now here again, if you notice, one point you will find common here. In most of the examples of positive deviation, we have alcohol. We have alcohol. Methanol in first, ethanol in second, methanol again in third, ethanol again in fourth, and ethanol again in last. Only the acetone carbon disulfide example you have to remember separately. But apart from acetone carbon disulfide, if you notice, in most of the cases we have alcohol. So you can remember it like this. If in a mixture you see that you have one compound as alcohol, then there is a high chance it will be a positive deviation from Raoult's law. Correct? And same like if you talk about negative deviation, so here we have hydrochloric acid water, nitric acid water, acetic acid water. Now, in the first three itself, you must have noticed that inorganic acid or organic acid with water, it will be forming negative deviation from Raoult's law. The reason behind that is, in negative deviation, just now you discussed, we have stronger attraction between the solute solvent particle. Now, in each cases, HCl, HNO3, acetic acid with water, there will be a formation of hydrogen bond, students, between the solute solvent, and that's why the attraction will be much stronger as compared to pure solvent. And that's why these are called negative deviation. Also, chloroform plus benzene, right? Acetone plus aniline, acetic acid plus pyridine. If you take out chloroform and benzene, this example, if you take out chloroform and benzene, then the rest cases, each of them, they are having negative deviation because of hydrogen bonding. I already told you that we have hydrogen bonding between H plus of HCl with water, HNO3 water, acetic acid water. Also, in case of acetone, the oxygen, aniline, the hydrogen, these two have hydrogen bond. Oxygen of acetone and hydrogen of aniline, they have hydrogen bond. Similarly, in acetic acid, the polar hydrogen will create a hydrogen bond with nitrogen of pyridine. So, in each example, in each cases, there is some point by which you can remember the examples, right? Ideal solution, same homologous series, similar functional group, right? Positive deviation, alcohol. Negative deviation, hydrogen bond. So these three terms, if you remember, it will help you in order to memorize it. But again, I am telling you, please note it down and revise it time to time, because this is important, students. It will be asked in your examination. So now I guess we have understood very well that what is ideal and non-ideal solution. Correct? So let's talk about some of the graphs we have in the non-ideal solution part. We have already seen that in case of ideal solution, because they obey Raoult's law, so the graph of vapor pressure of ideal solution will be according to Raoult's law. But when it comes to non-ideal solution, students, we saw that non-ideal solutions, they will not follow Raoult's law. Now, if they are not obeying Raoult's law, how we will be able to plot graph of vapor pressure for non-ideal solution having positive deviation or non-ideal solution having negative deviation? See, it will not obey Raoult's law, that's for sure, but we can plot the graph with help of Raoult's law, correct? Because in case of positive deviation, if you remember, if you go into the basics, I told you that in positive deviation, what will happen? The attraction between solute and solvent particle will be weak, right? Now please notice here, if the attraction between solute and solvent particle is weak, they can be easily vaporized. The solution I am talking about, because their attractions are weaker. And if they can easily vaporized, they will form more vapor pressure as compared to ideal solution, right? Like when you have an ideal solution. So in ideal solution, you saw that the total vapor pressure of solution will be P0 A chi A plus P0 B chi B. That was the case we had in the ideal solution according to Raoult's law. Here, in case of non-ideal solution, when you have positive deviation or when you have a weak attraction between the solute solvent particle, in that case, because the vapor pressure will be higher, you can write like this, that total vapor pressure will be more, that we can calculate from ideal solution or Raoult's law. Here the total pressure will be more than P0 A chi A plus P0 B chi B. And this will be exactly opposite in case of negative deviation. We saw that in case of negative deviation, students, the attraction between solute and solvent particle is stronger, right? Now, when the attraction between solute and solvent particles are stronger, what will happen? That solution, that particular solution will be very, very difficult to vaporize. So in this case, very less amount of vapors will be formed. So overall, the vapor pressure will be low. Why the vapor pressure is low? Because we have stronger attraction between the particles in the mixture. Right? So here what you can say that the total vapor pressure obtained will be less as compared to P naught A chi A plus P naught B chi B. P naught A chi A plus P naught B chi B will be the ideal vapor pressure, total vapor pressure in case of ideal solution. Right? So in negative deviation, total pressure will be low as compared to the ideal solution. In positive deviation, total pressure will be high as compared to the ideal solution. And now you can draw the graph very easily with respect to ideal solutions graph that we draw according to Raoult's law. See, if I plot chi A here, chi A is 0 here. So at the same point, you know chi B will be 1. At this point, if I say chi A is 1, so at the same point, chi B will be what? 0. Now, if I plot the graph for ideal solution for Raoult's law, so vapor pressure of A will be like this, straight line. And vapor pressure of B will be like this in the opposite direction, but again straight line. But this was the case of ideal solution. When it is positive deviation, in that case, the vapor pressure will be more, right? So this was for ideal solution. For positive deviation, non-ideal solution, the overall vapor pressure will go like this. More than the ideal. If you notice, it is more than the ideal case. Whether it is PA, whether it is PB. Whether it is PA, whether it is PB, in both the cases, the vapor pressure in this non-ideal solution will be more as compared to the ideal solution. And the same thing will be followed for the total vapor pressure. In case of ideal, total vapor pressure we represented from this line, this is straight line. But in case of non-ideal positive deviation, the total pressure will be also more as compared to ideal. And that's the reason we call it positive deviation. That's the reason we named it positive deviation. Why positive deviation? Because it is deviating positively with respect to vapor pressure, or it has more vapor pressure as compared to the ideal solution. And now I think after positive deviation, for negative deviation, you can draw the graph by your own now, right? Because in this case, the vapor pressures will be lower as compared to the ideal solution, correct? Like again, if I take chi A 0 here, so chi A will be 1 here, and chi B will be 0 here, so chi B will be 1 here. So graph of pressure of A according to ideal solution will be like this. Graph of vapor pressure of B according to ideal solution will be like this. And total vapor pressure according to ideal solution will be like this. We are just taking this for a reference, right? It's not the graph of non-ideal solution, it's graph of ideal solution. Now here, because we are having negative deviation, what will happen? The graph of non-ideal solution will be below the graph of ideal solution, or you can say like this, that our vapor pressure in this case is less as compared to ideal solution. So this is the graph of vapor pressure of A here, this is the graph of vapor pressure of B here, and this is the graph of total vapor pressure. Correct? So now I think you have understood graph of ideal as well as non-ideal, in that case positive and negative deviation. And see, from this ideal non-ideal solution part, you will be always getting conceptual problems, no numerical at all. Numerical in this liquid-liquid solution part, you will be always getting from that Raoult's law and Dalton's law point. So now let's understand a term, azeotrope, which is again related with your non-ideal solution itself. Students, first thing is here, try to understand what is the exact meaning of this azeotrope. Students, you know boiling point very well, right? Now, boiling point can be of two types. Boiling point can be of two types. Either it can be constant or it can be a range. Constant means if it has only one value. Like suppose if you talk about a pure liquid, like let's say water. So when you say boiling point of water, you say 100 degrees Celsius. So what is 100 degrees Celsius? It is value of one temperature, right? Or it is just a single value of temperature. So when for any mixture or any liquid, the boiling point has just one value of temperature, it is called constant or fixed value. On the other side, suppose if I say that there is a mixture A and B, mixture of A and B, and its boiling point is from 90 degree to 100 degree. So there I am saying that we have a range of boiling point, right? And here it means boiling starts at 90 degree and completes at 100 degree. So boiling point can have two types of values: constant, single value; range, range of value. Now, azeotrope means a mixture that has constant boiling point, that has one value of boiling point, just like pure liquids and all, right? So azeotrope you can define like this: constant boiling mixture. And of course, it is very hard to get a mixture which will have a constant boiling point, because most of the time a mixture will have a range of boiling point. And that's why this point becomes interesting and important for us, because it is hard to create a mixture which will have a one value or constant value of boiling point. But still we have, and that term is called what? Azeotrope. Right? So azeotrope is what? Constant boiling mixture. Now, for azeotropes, always remember that ideal solutions can never form azeotrope, because ideal solution, they will always have a range of boiling point, right? So ideal solution will never form azeotrope. So which one will form azeotrope? Your non-ideal solution, right? So when it is a non-ideal solution, so in that case, at some particular composition, you can get what? Your azeotrope, right? So whether it is a positive deviation from Raoult's law in case of non-ideal solution, whether it is a negative deviation from Raoult's law in case of non-ideal solution, in both the cases, you can obtain azeotrope at some fixed composition of solute and solvent. See, if we have a positive or negative deviation mixture, right? So it does not mean that those non-ideal solution will always form azeotrope. At a fixed composition, at a fixed ratio, at a fixed molar ratio only, they will form azeotrope, right? But whenever a solution having positive deviation, it forms azeotrope, so that is called minimum boiling azeotrope. Now, what is the meaning of minimum boiling azeotrope? Minimum boiling azeotrope means your mixture will have low boiling point as compared to both the parent liquids. So if you are mixing liquid A, liquid B, and the mixture has boiling point less than boiling point of pure liquid A, pure liquid B, then that mixture is called minimum boiling azeotrope. And the opposite of it, we call it maximum boiling azeotrope. And maximum boiling azeotrope means when the mixture has boiling point more than the parent liquid, Students, please notice here, sometimes in your exam, they will ask examples of positive deviation, negative deviation in terms of maximum and minimum boiling azeotrope. Like they will give you some compounds, their mixture, and they can ask which one is maximum boiling azeotrope, which one can form minimum boiling azeotrope. So you need to understand here that maximum or minimum boiling azeotrope, we will always decide on the basis of which one is positive deviation, which one is showing negative deviation. correct? So from azeotrope part also, you will be getting questions in your exam, right? And this azeotrope part, you should always revise time to time again, because that's important. And many students, they just forget the term that is azeotrope. They even forget to revise the term azeotrope, but it is again important for us. So now as we have understood what is azeotrope, what is ideal, non-ideal solution, let's see some of the questions that we get in the examination from the same topic. Can you do it, all of you? Try it first. Again, try before me. Question is, if I take 5 moles of liquid X and 10 moles of liquid Y. So here we have two liquids. One is liquid X, one is liquid Y. And we are mixing it in different amounts. X is 5 mole, Y is 10 mole. Very good. Now, we have prepared a solution. Now that solution has a vapor pressure of 70 torr. So they have given the vapor pressure of solution. So that means what? This is the total vapor pressure, right? After mixing X and Y, the total vapor pressure we are getting for the mixture is 70 torr. Very nice. Now let's read the question further. Question is, the vapor pressure of pure X and Y are 63, 78 torr respectively. Which of the following is true regarding the described solution? Now students, this question is based on comparison. You know what? For pure X, pure Y, if they have mentioned the vapor pressure and they have also mentioned the molar ratios or the moles values, you can calculate what will be the vapor pressure if they are forming ideal solution, correct? If I assume that X and Y is forming ideal solution. So assuming that, I can find out what will be the total vapor pressure if they are creating a ideal solution, right? And that can be done according to Raoult's law. P total equals to P naught. I will not write A here because here the compounds are X and Y. So let's write P naught X, chi of X plus P naught of Y and chi of Y. Everything is given. You can calculate the total pressure, assuming the mixture to be ideal. So P naught of X is 63. So 63 into mole fraction of X students, it will be the moles of X, which is 5 upon total moles. So total moles will be 5 plus 10, that means 15. So 5 upon 15 will be the mole fraction of X plus P naught of Y, they have given 78. So 78 divided by, not divided by, we have to multiply with mole fraction. So mole fraction of Y will be moles of Y, which is 10, divided by total moles, which is 15. Now just do the calculation. It's very simple. 5 3s are 15, and from 3 if you cancel it out, 3 2s are 6, 3 1s are 3. So 21 plus 5 2s are 10, 5 3s are 15. From 3 if you cancel it out, I hope it will cancel. 3 2s are 6, 1 8, 3 6 are 18. 26 into 2, 52. Now 52 plus 21 will be 73 torr. Now what's the point? Point is, I will get a 73 torr of pressure if the solution is ideal. But the actual solution is not ideal, students. The actual solution has vapor pressure of how much? 70 torr. Now if you compare, the vapor pressure of actual solution is less than if it were ideal solution. And you know what very well, that if the vapor pressure is lesser than the ideal solution, then we call it solution with negative deviation. Solution with negative deviation. So here ultimately what we got to know that a mixture of X and Y will form a solution having negative deviation from Raoult's law. Now see the options, you will definitely answer it. Whether the solution is ideal? No. The solution has volume greater than the sum of individual volumes? No. If the volume is greater, that means delta V should be positive. But you know that in case of negative deviation, both delta H, delta V has a negative sign, both decreases. So even B is not true. If you see option C, the solution shows positive deviation, again it is false. So ultimately the answer will be D. The solution shows negative deviation, correct. The solution shows negative deviation. So answer of this question, students, it should be D, and of course it is. It is D. And one more point, this question came in NEET 2025. So if you have already solved it, you solved a 4 marks question for your NEET examination. Correct? Now, let's see another question from the same topic, ideal and non-ideal solution. I hope this one you can do. If you have noted down those examples which I showed you, then definitely you will do it. Question is very simple. The mixture which shows positive deviation from Raoult's law. Positive deviation means the mixture in which the solute solvent attraction is weak as compared to pure solvent. And I gave you some tricks also to remember positive and negative deviation. So if you notice, you will find out that benzene toluene, acetone chloroform, chloroethane bromoethane and ethanol acetone. I hope you are giving the answer in the comment box for this question. I want all of your answers. Correct? So before looking at the answer part, answer in comment box, all of you. Definitely the answer will be D, because I gave you a hint that whenever you find it, alcohol is there, right? In this case, remember, we have ethanol. So I told you that if alcohol is there, high chance is that it will be a positive deviation. And obviously, if you talk about benzene toluene, they are from the same homologous series, so it will create ideal solution. Even if you talk about chloroethane, bromoethane, they have similar functional groups, right? So it will also create ideal solution. But acetone and chloroform, it will create negative deviation, because here we have a hydrogen bond between the oxygen of acetone and hydrogen of chloroform. You know very well that when we have hydrogen bond, it will show negative deviation, not positive deviation. So positive deviation will be shown only by ethanol and acetone. So now students, let's talk about the final part of this chapter. You know very well, I hope I should not mention that again. This chapter can be classified into 3 parts: gas liquid solution, liquid liquid solution and solid liquid solution. So now let's talk about the third part of the chapter, that is solid in liquid solution. Solid in liquid solution means what? When your solute is in solid phase and your solvent is in liquid phase. Students, here the first thing we should discuss is solubility of solid in liquid. What can be the factors on which solubility of solid will depend in liquid? Correct? So the very first point is, I already told you while I was discussing about gas in liquid solution, that we have a term called like dissolves like, and that term is even applicable in this case, right? Means what? If a solute is polar, then it will be more soluble in case of polar solvent. If a solute is non-polar, then definitely it will be more soluble in case of non-polar solvent. So polar, soluble in polar, non-polar, soluble in non-polar. That's the point. Now, apart from this, there is a very important factor that affects the solubility of solid in liquid, and it is none other than temperature. Please focus on this. Temperature can increase or decrease solubility of solids in liquid. See, in terms of gas liquid solution, what we noticed, in case of gas liquid solution, we noticed that when we increase temperature, the solubility always decreases. The solubility of gas in a liquid in water always decreases when you increase temperature. But in case of solid, the case is different. Here, by increase in temperature, right, solubility of solid in liquid can increase, or the solubility can also decrease. Now this depends on enthalpy of mixing for the process. Enthalpy of mixing for the process. When you dissolve a solid in liquid, and if the process is exothermic, the mixing process is exothermic, Means what? When you are mixing solid in liquid, so there is a release of energy, there is a release of heat, exothermic. So during exothermic mixing, if you increase temperature, then your solubility will decrease. Correct? So during mixing of solid in liquid, if delta H of mixing, it is negative, means exothermic mixing. So in that case, by increase in temperature, the solubility will fall. But if the mixing process is endothermic, so when you mix solid in liquid, that means during that process, heat is getting absorbed. So for endothermic mixing, if you increase temperature, then your solubility will increase. And I hope you all know very well that endothermic means the sign of delta H will be positive. So overall, for solid liquid solution, temperature can increase or decrease solubility based on what is the value of delta H mixing. Correct? Now with this, with the effect of temperature on the solubility of solid in liquid, now let's go into deeper and deeper inside this topic, inside the solid liquid solution topic. Now here, see, in your books you will notice that first we have colligative properties, then we have Van't Hoff factor. But I never recommend that. Students, you should always discuss first the Van't Hoff factor part. After Van't Hoff factor only, you should go into the colligative properties part. Because at the end, you know very well, in colligative properties also, we require this term Van't Hoff factor, and which is denoted by I, Correct? So, first of all, what do you mean from Van't Hoff factor? What is the meaning of Van't Hoff factor? Correct? So, it is somewhere related to a term from class 11th, first chapter. Students, I hope you remember it, that in the mole concept chapter of class 11th, we do talk about what is molecular mass, and what is molar mass. Correct? Basically, both are related to molecules, but when you talk about mass of single molecule, mass of one molecule, so mass of one molecule is called as molecular mass. But when you talk about mass of one mole of molecules, mass of any number of molecules, right? So mass of any number of molecules is called as molar mass. Correct? Now, the point is, why we are talking about molecular mass and molar mass here? Because this term Van't Hoff factor is connected with the term molar mass. You know, students, what happens here? A very interesting thing. When you take a compound in the pure state, suppose I have taken, let's say H2SO4. I have taken H2SO4 in the pure state. Now, when it is in pure state, that means what? Suppose that this is the container in which I have stored pure H2SO4. So in pure H2SO4, I will be having molecules of only H2SO4. No other molecule is there, only H2SO4 molecules are here. Right? Now suppose in the pure H2SO4, the molar mass is capital M. In the pure state, the molar mass of H2SO4 is capital M. Now what happens? If you prepare a solution of the same H2SO4 with some solvent, let's say that now I am dissolving H2SO4 into water to prepare a solution. Correct? So in the solution, now you will have molecules of H2SO4, but apart from H2SO4, now you also have molecules of water in it. Correct? Now the point is, the molar mass of your solute may change during the dissolution process. In the pure state, the molar mass of H2SO4 was M. Now as soon as you mix it in water, the molar mass of H2SO4 may change, can change. Correct? Now, if I am saying that our molar mass is changing in this case, so the new molar mass of H2SO4 in the mixture is now M dash. Is now what? M dash. Now, this ratio is defined as Van't Hoff factor. This ratio is defined as what? Van't Hoff factor. Van't Hoff factor here, I can say it is M upon M dash. M means what? Molar mass in the pure state. M dash means what? Molar mass in the solution. In your books, you also call it the molar mass in the pure phase. You also call it as normal molar mass. You also call it normal molar mass. And the molar mass that we have in the solution for the same compound, you also call it as abnormal molar mass. Right? So now I think you have easily understood what is the meaning of one-top factor, right? Normal molar mass upon abnormal molar mass, or molar mass in the pure state divided by molar mass in the solution. But the next question arises here is, sir, why the molar mass is changing? Why it is changing? Right? That's the question. Can you answer it by your own? In the comment box again? I hope yes. If no, then listen carefully. Students, molar mass will change because of dissociation or association of the molecule in solvent. If your solute, if your compound is getting dissociated or associated when you are dissolving it in a particular solvent, so due to dissociation association, the molar mass will change. Right? And if no dissociation association is happening, in that case, molar mass will not change. There are compounds which can dissociate, there are compounds which can associate, and there are compounds which will neither dissociate nor associate. We have all kinds of compound in our example. Correct? But always remember that the change in molar mass occurs because of dissociation or association. Let me give you some examples here. Suppose that you take CH3COOH, or why always CH3COOH? Let's take HCN, hydrogen cyanide. If you dissolve it in water, it will decompose like H plus ion and Cn minus ion. So here I can say that this particular electrolyte or compound or solute is having dissociation in water. So first thing is, if dissociation is happening, that means its molar mass will change. Now also, dissociation means loss of particle. Please focus on this point. Whenever dissociation will happen, your molecule will lose some atom, some ion, correct? And if it is losing some atom, some ion, its molar mass will decrease. Its molar mass will decrease. So, first thing is, during dissociation, your molar mass will change. M, pure molar mass, M dash, molar mass in the solution. These two will be different. And due to dissociation, due to loss of atom, the new molar mass will be smaller as compared to the pure molar mass. So here you can say that M is greater than M dash. Now in this case, if you are going to calculate one-top factor, just for a comparison, M upon M dash, so M is greater. And if numerator is greater, then obviously the value will be greater than 1. So always remember, in case of dissociation, one-top factor should be greater than 1, because new molar mass is smaller as compared to the molar mass in the pure state. Now suppose that if I talk about acetic acid, students, if you dissolve acetic acid in solution of benzene, your solvent is benzene. So in benzene, the acetic acid, it will not dissociate. Acetic acid can dissociate, but in water. In water. In benzene, if you dissolve this acetic acid, what happens? It will dimerize due to hydrogen bonding. It will dimerize due to hydrogen bonding. Two particles of this molecule will combine to form a single particle like this. Correct? So during association, there is a gain of atoms, right? And due to gain of atoms in a particular molecule, the molar mass will increase. So first thing is, whenever we have association, so during association also molar mass will change, and in this particular case, if you compare normal and abnormal molar mass, so abnormal molar mass will be larger, M dash will be larger. And here if you try to calculate one-top factor, because M dash is larger, so M upon M dash will become smaller than 1. So during dissociation, one-top factor is greater than 1. During association, one-top factor is less than 1. Now, if there is a no dissociation association, right, we have molecules. Please remember that, because sometimes in questions you will be getting these solute, sucrose, glucose, urea. These are some of the compounds which will not dissociate or associate. So their molar mass in the pure state in the solution will be same. And if m and m dash are equal, that means in these cases your Van't-Hoff factor will be 1. So now I think you have understood that why that particular molar mass is changing and where we can have Van't-Hoff factor greater than 1, less than 1 or equals to 1. So after understanding this, the next thing we have to do regarding the Van't-Hoff factor is their calculation. Because even in the colligative properties part, whatever question you do, most of the time you will have to find out Van't-Hoff factor. You will have to calculate Van't-Hoff factor. So let's now talk about how we can do the calculation, right? How we can calculate the Van't-Hoff factor for both the cases, right? We will talk about dissociation also, we will talk about association also. But there is a prerequisite again. In this chapter, especially during the calculation of Van't-Hoff factor, you should have a little knowledge of the ionic equilibrium chapter. Students, you should be aware about degree of dissociation of any electrolyte, especially weak electrolyte, correct? And same in case of association, you should know about degree of association. Now the point is, suppose if I take an electrolyte like HCN again, right? You know that in solution it will decompose into H plus and Cn minus, and I have to calculate its Van't-Hoff factor. So how it can be done? Suppose initially before dissociation I took total n moles of HCN before dissociation. So before dissociation, when no dissociation has happened, the moles of ion, the amount of ions will be what? 0. Now if I say that HCN, it has a degree of dissociation of alpha. So degree of dissociation, if it is alpha, so that will give you how much amount is getting dissociated. Whatever initial amount is there, if you multiply that with degree of dissociation, so that is your dissociated amount. So here, if degree of dissociation is alpha and initial amount I have taken n mole, so dissociated amount will be n into alpha. So out of n mole, n alpha mole will be dissociated. So I can say that after dissociation here, HCN will remain n minus n alpha. N was initial value and n alpha is getting dissociated. And according to stoichiometry, students, I can calculate that by dissociation of n alpha moles of HCN, how many moles of H plus or Cn minus will be calculated, will be formed. So 1 mole of HCN can produce 1 mole of H plus, 1 mole of Cn minus. So n alpha moles of HCN after dissociation, it will produce n alpha moles of H plus, n alpha moles of Cn minus. This is the first thing you have to do while calculating Van't-Hoff factor. You have to calculate after dissociation what are the number of moles of molecules and ions. And obviously initial you have to assume n. You can assume 1 also, that's fine. Now to calculate Van't-Hoff factor, what you have to do, you have to just find the ratio of number of moles after dissociation upon number of moles before dissociation. Like in this case, the total number of moles of all the particles are n minus n alpha HCN, n alpha H plus, n alpha Cn minus. So this is the total number of moles after dissociation divided by initial total number of moles. So here initial total moles are n plus 0 plus 0, that means n. You can do the further calculation, but it will differ electrolyte wise. Like this expression we are getting for HCN. If you take some other electrolyte, so then your expression will be different according to the stoichiometric ratio. Correct? But what you can do here, you can remember a short formula to calculate Van't-Hoff factor in case of dissociation. Students, if you want, you can do like this. You can do the calculation of Van't-Hoff factor by the proper procedure, the proper technique. But if you don't want to do like this, you can do it according to this formula. Van't-Hoff factor can be 1 plus n minus 1 into alpha. So this is a short formula we have. Want of factor is 1 plus n minus 1 into alpha. Alpha, you know, it is your degree of dissociation, and n is total number of ions that we have in one molecule of electrolyte. Like in case of HCN, one HCN has two ions, one H plus, one Cn minus. So for HCN, the value of n will be 2. If you talk about NaCl, so for NaCl, the value of n will be 2. If you talk about aluminium sulfate, Al2SO4 whole thrice, so in one Al2SO4 whole thrice, we have 2 aluminium ion and 3 sulfate ions. So total ions will be 5. So for the same aluminium sulfate, the value of n will be how much? 5. Correct? So like this, you can calculate want of factor in case of dissociation. Now, in the same way, you can do it for association also. Everything will be same. Everything will be same. Let's take example of that acetic acid case, students, where it was dimerizing in the benzene solution. If you take acetic acid, you dissolve it in benzene. So two particles of this will combine to give you a dimer, CH3COOH whole twice. So here see, dimerization means what? Dimerization means 2 moles will combine to give you 1 mole, or 2 particles will combine to give you one particle. Similarly, we can have trimerization, tetramerization. Trimerization means 3 particles will combine to give you 1 particle. Tetramerization means 4 particles will combine to give you 1 particle. Correct? But the point is, suppose here if I take n moles initially for this acetic acid, so again initially this is 0. Now in this case, if the degree of association, now let me call it beta, some other term, not alpha, because alpha I have used for degree of dissociation. If for acetic acid, degree of association is beta, so that means what? Beta into n, again degree of association into initial amount will give you what amount is getting associated, right? So beta into n, that means n beta part here, it will associate. So after association, out of n beta is associating, it will remain how much? N minus n beta. And again from stoichiometry you can find the product, right? 2 moles of this can produce 1 mole of this. So n beta mole of this can produce n beta by 2 moles of product. And again the technique is same. Here also want of factor will be total moles after dissociation divided by total moles before dissociation. So in this case, if I just write the expression, it will be total moles after dissociation, which is n minus n beta plus n beta by 2 total moles, right, divided by initial moles. So n plus 0, it is n. Now if you know what is beta, because n will be cancelled in both the cases, here also, here also. If you know alpha, in this case you can find want of factor. If you know beta, in this case you can find the want of factor. So in the question part, we will be looking at how we can find want of factor, but I hope that you have understood what is the technique to find want of factor. And if you want, for dissociation case, you can apply this formula directly to get the want of factor value. Correct? So after understanding want of factor, let's come to the next point from where you get question almost 90% time in your exam. And again, we get questions from this most of the time, but it is the easiest part of this chapter because we have some 3 or 4 formulas in it, and most of the time you get formula based question, direct formula based question, right? The topic is colligative properties. Colligative properties. So first, students, let us understand what is the meaning of colligative property. Right? See, the properties of solution or solvent, properties of solution or solvent, which depends on amount of solute present in the solution. Correct? So, you know physical properties very well, right? Physical properties means density, solubility, correct? Melting point, boiling point, freezing point, vapor pressure. All of these are physical properties, correct? But there are some physical properties of solution or solvent which depends on amount of solute. Those properties are termed as colligative properties. Those properties are termed as colligative properties. So basically colligative property is a physical property, right, which changes by changing the amount of solute. But here we never use that term physical property, we always call it colligative property, correct? Because we never write boiling point, freezing point or melting point or vapor pressure directly as colligative property. If you say that boiling point is a colligative property, then you are absolutely wrong. We have given different terms. So boiling point, melting point, freezing point, vapor pressure, they are physical properties, correct? But when you say relative lowering in vapor pressure, depression in freezing point, elevation in boiling point, osmotic pressure, so then they are termed as what? They are colligative properties. So in one line, please remember that colligative properties are those properties which depends on amount of solute. So those properties will change when you change amount of solute in a solution. When you change amount of solute in a solution. So one by one, we will look into each and every colligative property. Total we have 4, right? And the very first one is relative lowering in vapor pressure, right? So first, please try to understand this statement. Please break the statement to understand it more clearly. Students, if you talk about vapor pressure, so this term vapor pressure is a physical property of certain liquid or solution, right? Vapor pressure is physical property. When you say lowering, so lowering means what? Lowering means decrement. So somewhere we have a decrement in the vapor pressure. And relative means what? Relative means comparison to the original value. Whenever something is changing, right? So whatever change is there, if you compare that by initial value, so then it is called relative change, correct? So somewhere we have decrease in vapor pressure and its relative value is a colligative property. Now let me explain it by taking some example, right? Some diagrams and all, some containers and all. And you know that vapor pressure is an important term, right? Again we got vapor pressure. Vapor pressure was there in the liquid solution part also, Raoult's law and all, correct? Students, please see, if you take a container, inside that you take a pure liquid like water, again, because it is universal solvent. So for pure water, you can easily find out what is the vapor pressure. You boil it, correct? In equilibrium between liquid and vapor, whatever vapor pressure is there, you can measure it. So let's say that when it is pure water, the vapor pressure is P0. The vapor pressure is P0. Now, the point is, when you dissolve some solid particles in it to prepare a solution. Now, I dissolved some solid particles in it. So now it is not pure water. We have water, but apart from water, we have some solid particles inside the H2O molecules. Correct? Now, if these solid particles, they are non-volatile in nature. They are non-volatile, means they cannot be easily vaporized. What will happen? As soon as you add non-volatile solid particles in a liquid, its vapor pressure will decrease. And the reason is very easy. Because the surface area will be covered by some of the non-volatile particles, right? So the volatile molecule, H2O molecule, it will have a low surface, less surface to get evaporated for vaporization, correct? So whenever in a volatile liquid you add non-volatile solid particle, its vapor pressure will decrease. Now let's say that here also I calculated the vapor pressure and I got P here. Now ultimately, P will be smaller than P naught. P will be smaller than P naught. A pure solvent has always more vapor pressure as compared to the solution. So P naught will be greater than P here. Now, can you tell me what is the change in vapor pressure, students? If initially it is P naught and after decrement it is P. So change in vapor pressure, you can say here it will be delta P and it will be P naught minus P. So try to understand this P naught minus P term or delta P term can be called as lowering in vapor pressure, right? But when you divide this delta P with the initial value P naught, then it is called relative lowering of vapor pressure. So this particular term delta P upon P naught, this mathematical term delta P by P naught is called as RLVP, relative lowering in vapor pressure. And this term is a colligative property. Vapor pressure is not colligative property. This term is colligative property, delta P by P naught. And because it is colligative property, so it should depend on amount of solute. And we write mathematically it like it should be equals to mole fraction of solute. So when you equate this by this concentration term mole fraction, you are establishing a relation between the amount of solute and delta P by P naught. So please note down this formula, delta P by P naught equals to mole fraction of solute, or you can also write it like P naught minus P upon P naught equals to mole fraction of solute. Now what will happen here? From this formula, you will be getting direct numerical quotients. Direct numerical quotients. Now one more thing is there. This particular variation in the vapor pressure can be understood graphically also. You can understand this from graph as well. Suppose that I have plotted a graph between vapor pressure and temperature. I told you at the start when I was explaining vapor pressure that with increase in temperature of particle, your vapor pressure will increase. Now here if you notice, we have two curves. One curve is this, A to B, and one curve is this, C to D. So if I ask, out of this AB curve and CD curve, which one is representing solvent and which one is representing solution? So your answer should be the AB graph is for solvent and the CD graph is for solution. Why? Because at any particular temperature, if you notice, the vapor pressure of solvent should be more as compared to vapor pressure of solution. So graphically, between the graph of vapor pressure and temperature, the graph of solvent will be always above the graph of solution. I hope this much part you have understood, that the graph of solvent will be above the graph of solution because solvent has always more vapor pressure as compared to solution. Correct? But always remember this formula because from here you will be getting numerical quotients. Correct? Now, after relative lowering in vapor pressure, the next colligative property we have is elevation in boiling point. Again, please try to break down this statement to understand it more clearly. Students, what is boiling point? Boiling point of any liquid is a physical property again. Boiling point is physical property. But when you say elevation in boiling point, so elevation in boiling point is a colligative property. And again, elevation means what? A kind of increment. Elevation means increment. So somewhere this term is saying that we are having increment in boiling point. Elevation in boiling point. Now here what happens? Now I am not going to draw those diagrams of pure solvent and solution. You can imagine that in your brain now, right? That much you can do, all of you, correct? So suppose that I have a pure solvent, correct? So a pure solvent will have a boiling point. Let's say that the pure solvent has boiling point of TB naught. This is the boiling point of pure solvent. Now, when I add some non-volatile solid particles, some non-volatile solute particles in the solvent, right, its boiling point will change. Its boiling point will change. And because those particles are non-volatile again, right, their boiling point, the solution's boiling point will increase. as compared to pure solvent. Correct? So as compared to pure solvent, the boiling point of solution, which I am writing TB here, will be higher. Now, if I tell you, if I ask, what is the change in boiling point here? What is the change in, what is the increment in boiling point here? You will easily say, sir, it is TB minus TB naught, because TB is the boiling point of solution and TB naught is the boiling point of solvent, right? This is higher, this is lower. So this TB minus TB naught can be written as delta of TB, and students, this delta TB itself is called as elevation in boiling point. So again, this mathematical term delta TB or TB minus TB naught, this term is called as elevation in boiling point, and this particular term delta TB is your colligative property. Correct? Now again, because it is colligative property, so we will have to relate it somewhere with the amount of solute, and it is related by the concentration term molality, small m. Right? The mathematical formula for delta TB can be delta TB is I Kb into molality. Again, delta TB is your elevation in boiling point. I, just now you saw, I is your Van 't Hoff factor, and this small m is your molality. Now this Kb, students, it is a constant. Here it is called ebullioscopic constant. Ebullioscopic constant. Or sometimes it is also called as molar elevation constant. You know how it named molar? Because we have molality, so molar, and we are having elevation, so elevation. So ebullioscopic constant is also called as molar elevation constant, Kb, and it depends on nature of solvent. Always remember that. Sometimes they can ask it in the statement type problem. So Kb always depends on nature of solvent. It has nothing to do with solute. It has nothing to do with solute. Its value depends completely on the solvent and temperature, right? Sometimes even for Kb, they can ask a separate calculation. You should remember even the formula of calculation of Kb. Please note it down. Kb can be calculated as Rm T square upon 1000 delta H. R means, you know, gas constant. M is the molar mass of your solvent. Here T, because we are dealing with boiling point, so this is your boiling point of the solvent. 1000, and this delta H, again we are dealing with boiling point, so this delta H is enthalpy of vaporization. Enthalpy of vaporization. So they don't ask much questions from this, but I think you should be ready. Even they ask question from this formula Kb, you should be able to do that. So note down delta TB, I Kbm, and also note down Kb equals to Rm T square upon 1000 delta H. And again, elevation in boiling point can be also understood graphically. Students, again we have a graph, just like previous one, between vapor pressure and temperature. And again we have plotted solvent and solution. Now I don't have to tell you that the upper graph AB, it is for solvent, and the lower graph CD, it is for your solution. Now students, if you remember the definition of boiling point, so it is the temperature of a liquid or solution when the vapor pressure becomes 1 atm. So point is, when you take a liquid or solution and you start heating it, you start increasing the temperature. So with temperature your vapor pressure will also increase. So when the vapor pressure becomes 1 atm, so at that particular moment, whatever your temperature is, so that temperature is called what? Boiling point. Now in this case, suppose that at this point, vapor pressure is 1 atm, correct? So at this point, whatever corresponding temperature is there for both the graph, that will be your boiling point. So this point X on the solvent's graph will tell you the boiling point of solvent. So this point is boiling point of solvent, and this point Y will give you the boiling point of your pure solution. And graphically also, if you notice, you can say that the boiling point of pure solution is higher as compared to the boiling point of pure solvent, which I discussed earlier, which I told you earlier. But ultimately, the summary of this topic is you have to just remember this formula, because from here you will be getting a lots of numerical questions. Right? After elevation in boiling point, we have a completely similar term. Especially why I am calling it similar, on the basis of formula. So here, before explaining it, let me write the formula first. Because you know what? Depression in freezing point, which is a colligative property, if you try to calculate it, so the formula for depression in freezing point in terms of colligative property is delta Tf equals to I Kf into molality. Isn't it quite similar to the elevation in boiling point? In elevation of boiling point, we have I Kb molality. Here we have I Kf molality. Correct? So first let's understand this also. Freezing point, again, it is a physical property. But when you say depression in freezing point, see, depression means what? It's not depression, it's decrement, right? Depression means decrement. So somewhere we are saying that for a solvent, the freezing point will decrease when a non-volatile solid particle is added. Freezing point will decrease here. So once again, if I tell you that T0F is the freezing point of pure solvent, after adding solute, now the new freezing point is Tf. So here I am saying that by addition of solute particle, your freezing point will decrease. So that means what? The pure freezing point will be more as compared to the freezing point of solution. Now here also, if I try to get the change, what is the change we are having in the freezing point? So change will be, in this case, Tf naught minus Tf, because in this case Tf naught is larger, Tf is smaller. So change in freezing point, Tf naught minus Tf, can be written as delta Tf, and students, here this delta Tf, this mathematical term is called as depression in freezing point. So depression in freezing point is delta Tf, elevation in boiling point is delta Tb. Now this delta Tf, because it is colligative property, it can be written as Van 't Hoff factor into Kf into molality. In this case, Kb was ebullioscopic constant, and this Kf is called cryoscopic constant. Cryoscopic constant. And this Kf also depends on nature of solvent. Even Kf has similar formula to that of Kb. Kind of same formula we have. If you try to get Kf separately, so Kf is R m T square upon 1000 delta H. But because here we are dealing with freezing point, so this temperature is freezing temperature, right? And we are dealing with freezing point, so this delta H is delta H of fusion, delta H of melting, correct? So for both Kb, Kf, we have same type of formula, so that will help you to remember the formulas of Kb, Kf. Both Kb, Kf depends on nature of solvent, right? And Kb is called ebullioscopic constant, while Kf is called cryoscopic constant. Also, this cryoscopic constant can be called as molal, because we have molality, depression constant. So Kb is molal elevation constant and Kf is molal depression constant, right? And even that freezing point depression can be understood graphically. Again, all of you, I hope you all have a basic idea regarding freezing point, right? Freezing point is the temperature at which your liquid starts converting into solid. So in this case, again we have plotted graph between vapor pressure and temperature. But in this case, you will notice a sudden shift in the diagram, in the curve. Like the upper curve, again it is for solvent. If you notice, and please try to understand this backward. Try to look at this curve backward from right to left. If you go from right to left, you notice that your vapor pressure is decreasing. Why? Because you are decreasing the temperature. In this curve, if I go from left to right, that means my temperature is increasing. If I go from right to left, then my temperature is decreasing. So if I am decreasing the temperature, the vapor pressure will gradually decrease. Now, at this particular point, if you notice, the vapor pressure has a large sudden decrement. Large sudden decrement. Now this happens when your liquid starts converting into solid. So students, here this is the point where your solvent starts freezing. So at this point, whatever temperature is there, TF naught, it is the freezing point of pure solvent. Similarly, if you talk about solution whose graph is just below the solvent, again if you go from right to left, you decrease the temperature, right? Vapor pressure at this point, again it has a sudden decrement. So that means what? So again at this point, the vapor pressure is suddenly decreasing. That means what? Again I can say that at this point, the solution has start freezing. And let me tell you one thing. You say that your solution freezes, but actually solution does not freezes. In the solution, the solvent part starts freezing, right? But here, if you notice, this temperature is below this T naught F. This temperature, this freezing temperature for the solution is below the freezing temperature of pure solvent. So that's how from the graph also you can understand that our freezing point is shifting from right to left when I go from pure solvent to solution, right? And graphically, this term, this temperature difference on the graph is your depression in freezing point. So now I think we have understood depression in freezing point very well, and now we have the last colligative property, which is osmotic pressure. But students, here, before going into osmotic pressure, you will have to understand a process. You will have to understand a process. That process is osmosis. I think in biology also you must have studied osmosis. But let me warn you something. In biology, most of the time, the definition of osmosis is reverse. Because in biology, we talk about concentration of solvent most of the time. But in chemistry, whenever you say concentration, so by default, you mean it as a solute's concentration. More concentration means more solute's concentration, more amount of solute. So that's why you may find a difference or opposite definition between the osmosis for bio and chemistry. So in chemistry part, osmosis is a process, very easy process although. What it says that the net flow or overall flow of solvent particles through semi-permeable membrane. In short, semi-permeable membrane can be written as SPM. See, semi-permeable membrane, they have very, very small porous holes. So they allow the solvent particles to pass through it, but they do not allow the solute particles to pass through it, right? That is semi-permeable membrane. So the net flow or overall flow of solvent particles through semi-permeable membrane from low concentrated solution to high concentrated solution. And please understand here, when I say low concentration, means the one which has less amount of solute. And when I say high concentration, so that means what? The solution which has more amount of solute. So overall osmosis is when you separate two solution with help of semi-permeable membrane. So see, solvent will pass from both the sides. You can't stop that. Solvent will pass from high to low, low to high. But the net flow or overall flow of solvent will be from the low concentrated solution to highly concentrated solution. And that process is called osmosis. Let's try to understand this easily with help of a diagram. Students, suppose that I have taken a container, right? And I have separated with a partition of a semi-permeable membrane. This is my semi-permeable membrane. Now, Instead of taking low concentrated, high concentrated solution, in this case, let's take one side pure solvent and on the other side pure solution, right? So on the one side, I have taken pure water, and on the other side, I have taken water mixed with some solid particles in it. So this is my solution. Now obviously, on the left hand side, if I have taken pure solvent, so here the concentration of solute will be low, and if it is a solution, so as compared to pure solvent, the solution will have a high concentration. So here net flow of solvent particle will be from low to high, from pure to solution, left to right. This process is called what? Osmosis. So I hope that osmosis is clear to you. Now let's come to that osmotic pressure thing. Please listen carefully. When osmosis is happening, the solvent particle is passing through semi-permeable membrane from low concentrated to high concentrated solution. Now suppose that I want to stop it. I want to stop this flow of solvent from left to right in this case, left to right in this case. So to stop osmosis, what I can do, I can take a piston, I can apply pressure on this. So when I will apply pressure on this part of solution, basically I will hinder the flow of water, the flow of solvent. I will not allow this piston to move up or for this solution to increase the volume. So then what? The flow of water will stop. So on the solution part with respect to solvent, or when you have low high concentration, so in that case, when you apply pressure on the high concentration part, correct? So by applying pressure, what we can do, we can resist the osmosis, right? Now, that sufficient pressure or that minimum pressure which completely stops your osmosis, which is applied on the solution, that pressure itself is called osmotic pressure. That pressure is called osmotic pressure, and it is denoted by what? Pi. And because this pi, osmotic pressure, is a colligative property, so mathematically it can be expressed as I C R T. I want a factor, C is your molarity, mole per liter for the solution, R is gas constant, and T is your temperature. So for any solution, we have its own osmotic pressure pi, and that can be calculated as want of factor into molarity into R into temperature. Now the point is, for this solution, if osmotic pressure is pi and I am applying P pressure, if the applied pressure is equals to pi, then your osmosis will stop. No osmosis will happen, because that's the definition of osmotic pressure. But suppose if the applied pressure, whatever pressure I am applying, if it is less than the osmotic pressure, if it is less than the required pressure to stop osmosis. So if your applied pressure is less than osmotic pressure, in that case, the rate of osmosis will be slower, the rate will decrease, but eventually you will be unable to stop osmosis. In that case, osmosis will happen if the applied pressure is less than osmotic pressure. But a very interesting point is here. Suppose if your applied pressure is more than osmotic pressure, if you have applied enough pressure, then osmosis will be reversed. Osmosis reversed means now the solvent will move from high concentration to low concentration, and that process we name it as reverse osmosis. We name it as reverse osmosis. So please note down this point, also the formula of osmotic pressure, correct? So applied pressure equals to osmotic pressure, no osmosis. Applied pressure less than osmotic pressure, osmosis will happen with a slower rate. And applied pressure greater than osmotic pressure, that means there will be reverse osmosis. I hope in your house, in your home, you must have seen the RO system, right? Water purifier. Now see, those water purifiers, they work on the basis of reverse osmosis. And that's why in short we call it RO, right? So now we are done with all the 4 colligative properties: elevation in boiling point, depression in freezing point, the osmotic pressure, and relative lowering of vapor pressure. In each case you have one formula, and from that formula only you get numerical questions in your exams. So now students, let's practice, let's do some questions from the colligative properties, and please take your pen paper because I want you to do each and every question of colligative property with me, right? So don't sit idle, don't be lazy, right? Apply some efforts in your studies, right? So take your pen paper and start solving these problems along with me. So the very first question from colligative property we have is, which of the following aqueous solution will exhibit highest boiling point? See, this is a question from elevation in boiling point, and here they are asking a kind of comparison for different solution. They are asking, first go into the logic of the question. First, let's talk about the logic of question. Logic is, they are asking which will exhibit highest boiling point. Now, from colligative property, we know that in boiling point, we always have elevation, right? And that elevation in boiling point, delta TB, is written as I KB into M. Now, the solution in which there is more elevation in boiling point, we have more value of delta TB, that particular solution will have more boiling point. So what I can say? I can say just calculate delta TB. The solution for which you are getting highest value of delta TB will have highest boiling point. But when you are doing comparison, right, especially if all of them are aqueous solution. See, if all of them are aqueous solution means in each case my solvent is water, and if my solvent is water, then in each case the Kb will be same. So instead of finding the whole delta Tm, what you can do, you can just find I into M, Van't factor into molality. And the one which will have higher value of Van't factor into molality will have higher value of delta Tb, will have higher value of boiling point. Correct? So one by one, let's check them. In the first case, 0.01 molar solution is there, and electrolyte is Na2SO4, right? So for Na2SO4, you can calculate Van't factor like 1 plus n minus 1 into alpha. But here, they have not mentioned alpha and all. So what we can do, by default, we can consider that salts are strong electrolyte. By default, not always, when it is not mentioned. So by default, you can assume that all the salts are strong electrolyte. And students, for strong electrolytes, alpha is 1. Alpha is 1. So for Na2SO4, if I calculate the Van't factor, it will be 1 plus N, 2 sodium, 1 sulfate. So total number of ions is 3 minus 1, and strong electrolyte alpha is 1. So this will come out how much? 1 plus 3 minus 1, which is 2. So 1 plus 2 is 3. So Van't factor is 3. One more thing is there. If you know that your electrolyte is strong, so for strong electrolyte, only for strong electrolyte, you can say directly number of ions is equals to Van't factor. Like in Na2SO4, if I have total 3 ions per molecule, 2 sodium, 1 sulfate. So for strong electrolyte Na2SO4, if I have 3 ions per molecule, then its Van't factor will be 3, which I got from the calculation also. But directly also you can say that for Na2SO4, Van't factor is 3. Similarly, if you talk about KNO3, potassium nitrate, it is also salt, it is also strong electrolyte here. Now in KNO3 you have 2 ions, K plus NO3 minus. So without calculation, directly you can say that in KNO3, because we have 2 ions, its Van't factor will be 2. Right? For urea and glucose, I told you to remember that for these cases, Van't factor will be 1 because they do not dissociate or associate. So I have the Van't factor of each, 3, 1, 1, 2. And I have the concentrations. Just multiply the Van't factor and concentration term. Don't worry, here you use molality. But for each case, if you use molality, or for each case for comparison, if you use molarity, the comparison can be done on the basis of molarity also, right? So 3 Van't factor, molarity 0.01. So I into M will be 0.03 for the first case. In the second case, Van't factor is 1, molarity is 0.015. So it will be 0.015. In the third case, Van't factor is 1. Molarity is 0.01. So 1 into 0.01 is 0.01. In the last case, Van't factor is 2. Molarity is 0.01. So 0.01 into 2 is 0.02. Now if you notice, the largest value of I into concentration is for the first one, 0.03. So definitely the one which has higher value of I into concentration will have higher value of delta TB and will have higher value of boiling point. So in this case, our answer will be 100% A. 100% A. And I think from this question you have also understood that for strong electrolytes, we can directly find out the Van't factor instead of using 1 plus n minus 1 alpha, or instead of doing that part of calculation where you have to see initial amount, final amount after dissociation. So those parts can be skipped, especially for strong electrolyte in case of dissociation. Now this question came in NEET 2025. So now you can understand what type of questions you get from the colligative property. With this, let's see another question from the same colligative property. First of all, you should always read the question carefully. Read the question always first, then do the calculation. Question is mass of glucose. So glucose is our solute here. Without going further, first thing I can say here is Van't factor will be 1 for this. Now, mass of glucose required to be dissolved to prepare 1 liter of its solution, which is isotonic with 15 gram per liter solution of urea is, again urea has Van't factor of 1, is, and molar masses of carbon, hydrogen, nitrogen it is given. See, here we have got a term, right? I hope you know this from again bio. Isotonic, hypertonic, hypotonic, correct? So when you say isotonic, two solutions are isotonic, that means they have same osmotic pressure. They have same osmotic pressure. Here if I am saying that the solution of glucose and urea is isotonic, that means both the solution will have same osmotic pressure, right? Now you know the formula of osmotic pressure, students. Osmotic pressure is what? I into C into RT, right? So for glucose, I is 1. For glucose, let us say molarity is M of glucose into RT. And for urea, again, Van't factor is 1. Let's say that for urea, molarity is Mu, just for representation, into RT. Now, if it is isotonic and if it is at same temperature, the RT term will be cancelled. So here isotonic means molarity of glucose should be equals to molarity of urea. Now, if you know the molarity of formula of molarity, you can solve it, right? You have to just put the formula of molarity in this. So molarity of glucose will be number of moles of glucose divided by volume of glucose solution, which was given 1 liter, So 1 equals to molarity of urea will be moles of urea. Now urea is 15 gram in 1 liter. So 15 gram means 15 upon molar mass of urea. If you calculate molar mass of urea, it will come out 60. I do remember because I have done so many questions. So for compounds like urea, glucose, I remember all the molar masses. Urea 60, glucose 180, correct? Sucrose 342. So mass upon molar mass, 15 by 60 is the number of moles of urea here. Upon 15 gram is in 1 liter. So again volume is 1 here. So from this, 15 fours are 60. You can easily get number of moles of glucose which is 1 by 4. And from moles you can find mass just by multiplying with molar mass. And just now I was telling, right, that molar mass of glucose is 180. So mass of glucose here, it will be number of moles 1 by 4 into 180. And if you solve it, it will be 4 fours are 16, 2 20, 4 fives are. Answer will be 45 grams of glucose. Answer will be D. Of course it is D. It can't be wrong. And this question again we got in the NEET 2024 examination. Correct? So these two questions are of different types, right? It was from isotonic or osmotic pressure, And the previous question we saw, that was from elevation of boiling point. And even the types of problem which I have included in this session, they are different, so as to give you different types of experience in the question, right? But you know that after this session, what you have to do, what is your task after me? You have to download all the DPPs we are providing in the description, and we have at the PW app. So download all those practice problems and solve it by your own. Correct? Then only you can say that we are done with the solution chapter. So now students, the next question we have is again from osmotic pressure, but it is a little bit of different question we have, right? Graphical question, if you notice. Question is, the plot of osmotic pressure versus concentration for a solution gives a straight line. Definitely it should be a straight line, because you know that the formula of osmotic pressure is I into molarity into concentration into RT. Now if I try to plot a graph between osmotic pressure and concentration, so I am doing what? I am plotting osmotic pressure on y-axis and concentration on the x-axis. So I into R into T will be my slope, right? So the graph is like straight line. They have already mentioned in the question. Now they are saying that straight line with a slope of 25.73 liter bar per mole. So for this straight line, they are saying slope is 25.73, and please focus on the unit. It is liter bar per mole, mole inverse. Correct? The temperature at which the osmotic pressure measurement is done. It's a very simple question. You know what? By comparison, you just saw that if I am plotting osmotic pressure and concentration on y and x axis, then I into R into T will be my slope. So I can directly write slope is equals to Van 't Hoff factor into R into T. Now slope is given how much? 25.73. 25.73. Now what is your compound? In this question they have not mentioned what is your compound. So by default what I can do, I can consider that my Van 't Hoff factor is 1, right? If it is mentioned you can find it, but if they have not mentioned what is your solute, right, then by default you should take Van 't Hoff factor as 1 always. It happens many times they will not mention the compound, so it's your task to judge it, right? That if it is not mentioned, so by default Van 't Hoff factor should be 1. So Van 't Hoff factor should be 1. R they have given, it is 0.083 and unit is liter bar mole inverse, the same unit here we have. So we can directly put 0.083 into T, into T. So we directly got temperature. It will be 25.73 divided by 0.083. Just divide, you will get your answer. And always the calculated value of temperature will be in Kelvin. Please remember that. The answer whatever you are getting, it will be always in Kelvin. So from Kelvin, if you want to convert into degree Celsius, so you will have to minus 273.15. Correct? So if you do the calculation further, definitely your answer will be 37 degree. But please remember, in any formula, when you put temperature, it is in Kelvin. From any calculation, whenever you got temperature, so that comes in Kelvin. So then it is your task to convert it from Kelvin to Celsius by minusing 273.15. Now, let's talk about our very famous Van 't Hoff factor. But sometimes what happens, from Van 't Hoff factor we get direct problem, direct calculation of Van 't Hoff factor like this. The Van 't Hoff factor for a dilute aqueous solution of a strong electrolyte of barium hydroxide. See, this question is a very direct question, right students? Because they are mentioning it is a strong electrolyte. You know that for strong electrolyte alpha is 1. More from that, I told you that in case of a strong electrolyte, you can directly say that Van 't Hoff factor is equals to number of ions, right? So the formula of barium hydroxide, barium group 2 element, it has valency of 2, hydroxide has valency of 1. So formula of barium hydroxide is BaOH whole twice. So in one barium hydroxide, if you notice, you have total 3 ions, 1 barium ion, 2 hydroxide ions. So if strong electrolyte is there, one molecule has total 3 ions, then definitely the Van't factor will be 3. No need to calculate. Even if you calculate, you will get the same answer. Answer will be D. And even this question, this easy question, we got in the NEET 2016 examination. Right? So, of course, from Van't factor, you will be getting direct questions in your examination, NEET examination. So now students, the next question we have is again from colligative property, but if you notice this time they have mixed two colligative properties together. If you read, if you sense the question, you will notice that in this RLVP and elevation in boiling point, both topics are combined. Correct? Question is, at 100 degrees C, the vapor pressure of a solution of 6.5 gram solute in 100 gram of water is 732 mm of Ig, Kb 0.5 to the boiling point of this solution will be. Right? First point is, the solute is 6.5 gram, the solvent is 100 gram. And for solution, vapor pressure is given 732 mm of Ig. Now, students, please remember that for pure water, the vapor pressure is always 760 mm of Hg. Please note it down because you have to remember it. Sometimes in questions they will not mention this point. For pure water, the vapor pressure is 760 mm of Hg. Now here, if I apply the formula of relative lowering of vapor pressure, that is P0 minus P upon P0 is equals to mole fraction of solute. So in this case, P0 for pure water is 760 minus P, vapor pressure of solution, they have mentioned 732 divided by again 760. Now this should be equals to mole fraction of solute. So here solute is 6.5 gram, right? So let me keep it as N, moles of solute, upon moles of solute N plus moles of solvent. Solvent is water. So 100 gram water, in moles it will be 100 by 18. 100 by 18. From here, what I can obtain the number of moles of solute. I can obtain the number of moles of solute. Right? Now, what they are asking, they have given the Kb value and they are asking the boiling point of solution. Again, boiling point of pure water, Tb0, it is 100 degrees Celsius, right? And we know that in boiling point, elevation will happen. And the amount of elevation delta Tb can be calculated as I Kbm. But again, because they have not mentioned the solute, by default, I will take Van't factor 1, correct? So it will be Kb into molality, correct? So from here, delta Tb I can find, Kb is given 0.52 into molality. Now, your task is, from this expression, calculate the number of moles of solute. And because weight of solvent is given, you can easily find the molality, right? If I do the further calculation, so 760 minus 732, it will be 10 minus 2, 8, 5 minus 3, 2. So this is 28 upon 760 equals to N upon N plus 100 by 18 is 5.55, right? Now, to calculate this, you need a little bit of time, hardly 1 minute. How to do it? Reverse it first, like 760 divided by 28, it should be equals to N plus 5.55. Everyone has their own method of calculation. I think that reversing it here will give you easy calculation, right? So 760 upon 28, if you solve it, I'm not going to do the whole calculation. 760 by 22 will be 22, 8 into 256. It will be nearly 27. Nearly 27. And N by N will be 1 plus 5.55. 5.55 divided by N. So N by N is 1, 5.55 by N I wrote separately. Now 27 minus 1 is 26. So it will be N equals to 5.55 divided by 26. Now 5.55 by 26 will be roughly, let me divide it, 5.55 divided by 26. So decimal 2, 52, 3, 5, nearly 1. So this is nearly 0.21, right? So this is the number of moles of solute, 0.21, correct? Now, As I have number of moles of solute, I have a weight of solvent 100 gram. I can separately find molality. Molality is number of moles 0.21 divided by weight of solvent in kg. So 100 gram in kg, it will be 0.1, correct? So 0.21 by 0.1, it will be roughly 2.1. I am doing round of calculation, but I hope I will get nearly same answer, right? So now my molality is 2.1. Delta TB will be 0.52 into molality, which is 2.1. Now 0.5 into 2 is roughly how much? 1 or 1 point something, 1.1 or 1.2, right? So if my delta TB is 1.1, T naught B is 100. So after elevation, the boiling point of solution will be 100 plus 1.1, which is near about 101 degrees Celsius. I hope the answer should be C here, because I have done a round of calculation. But yes, answer is what? C. So round of calculation is okay for me, but not for you. You always have to solve completely at least up to 2 decimal digits accurately, right? So here the answer is C, 101 degrees Celsius, and this question again came in the NEET 2060 examination. So now I hope that from colligative properties you have understood what types of variation you can get in the examination, right? So this is all about the solution chapter, students. I hope that I have helped you a little bit in your journey in this chapter, right? And from today onwards, you will always remember the full chapter, the whole chapter, like by classifying that into 3 parts, right? First of all, we have the chapter solution, classify into 3 parts: gas liquid, liquid liquid, solid liquid. Each part we have 2 topics to study: gas liquid solubility, Henry's law; liquid liquid Raoult's law and ideal non-ideal solution; solid liquid solution, van 't factor, colligative property. Apart from these 3 parts, separately you should focus on concentration terms, but I hope that concentration terms you are focusing from your class 11th itself. So up to this time you are very good in your concentration terms part, correct? And keep practicing those DPPs that we are providing, correct? And that is of course your homework. What is your homework? Your homework is to practice more and more problems, and especially in the solution chapter, try to solve both types of questions. It's a physical chemistry chapter. That doesn't mean we need to do only numericals. In this chapter, you have to do numericals also, and also the conceptual problems, especially from ideal, non-ideal solutions, right? Henry's law, solubility part, Henry's constant part. So both numerical and conceptual problems are there in this chapter, and you should practice both of them. And where you can find all those types of problems? In the DPPs that we are providing, right? So download PW app, keep practicing, keep rocking. Thank you very much, and I hope that you all will rock in the NEET examination. Bye bye, over and out, take care.